At the smallest scales ever explored, matter no longer behaves in the quiet, predictable way everyday experience would suggest. Outcomes refuse to settle into single answers. Properties appear only through interaction. This journey moves slowly through that landscape, not to force conclusions and not to simplify what resists simplicity, but to trace the shape of quantum reality with care, to understand what can be known, what can be measured, and where certainty naturally gives way to probability. Patterns emerge that follow clear rules, yet resist simple cause and effect. What seems stable from a distance becomes fluid up close, guided less by certainty than by tendency. Welcome to the Sleepy Scientist. If you enjoy drifting through questions that lie far beneath everyday experience, you're very welcome to settle in and let these quiet explorations unfold. At these deeper levels of reality, familiar expectations loosen without effort. The solid world suggested by touch and sight softens into something less definite. Certain things, location becomes approximate, motion no longer traces clean paths, but spreads into ranges of possibility. Even the idea of an object existing entirely on its own begins to blur, its boundaries losing the sharpness they seem to hold at everyday scales. For over a century, physicists have explored this subtle territory with instruments built for extraordinary sensitivity, detectors capable of registering individual particles of light. Systems cooled until motion nearly disappeared. Mathematical descriptions refined again and again, not to satisfy intuition, but to remain faithful to what experiments consistently reveal. What has emerged is not disorder, but a different kind of structure, one that resists everyday logic, yet proves remarkably dependable. Predictions confirmed with extraordinary precision. Technologies built upon principles that feel counterintuitive, yet perform their roles quietly and without fail. Laboratories and research institutions around the world continue to refine this picture, extending measurement, increasing control, and probing ever more delicate regimes. With each improvement, the view becomes clearer, even as its deeper implications become more subtle rather than more certain. The transition from a world of solid edges to a world of quantum possibilities is not a sudden drop, but a gradual softening of everything we think we know. Consider how you perceive objects around you in the room, a chair, a book, the very floor beneath your feet. To your senses, these things are absolute. They occupy a single point in space and they remain there until moved. But as we begin to drift downward, past the layers of visible matter and into the microscopic, that sense of absolute position begins to melt away. It is as if the universe, when viewed through a powerful enough lens, loses its focus. This lack of focus is not a flaw in our vision, but a fundamental characteristic of the fabric of reality itself. In the quantum landscape, an electron does not sit in a specific spot like a seed in an apple. Instead, it exists in a state of potential, a cloud of maybes that only resolves into a yes when we interact with it. This shift in perspective requires us to let go of the need for rigid answers. It invites us to be comfortable with the approximate. If you find your mind trying to grasp for the old certainties, gently remind yourself that they were only ever approximations for the human scale. Here, in the quiet depth of the subatomic, we are learning a new language. It is a language of tendencies and waves, where things are not here or there, but rather more likely to be found in one region than another. There is a profound peace to be found in this lack of rigidity. As we settle further into this exploration, consider the history of how we arrived at this boundary. For centuries, the pillars of classical physics stood tall and unquestioned. They told a story of a clockwork universe, a grand machine where every gear turned with perfect predictability. If you knew the position and velocity of every particle, you could, in theory, map out the entire future of the cosmos. It was a comforting thought, providing a sense of total mastery over the material world. But the universe had secrets that the clockwork model could not contain. Small discrepancies began to surface in the late 19th century, whispers from the dark that suggested the machine was not as simple as it seemed. These were not errors, but invitations to look closer. When scientists finally looked past the gears and into the heart of the atom, they they found not smaller gears, but a shimmering, probabilistic reality that defied every classical law. This discovery did not break the universe. It simply revealed that the laws we had cherished were merely the surface ripples of a much deeper ocean. The transition from the clockwork model to the quantum model is like moving from a world of sharp black and white drawings into a world of vibrant, overlapping watercolors. The edges are gone, but the beauty and the order remain, expressed in a more complex and elegant way. The instruments we use to probe this landscape are themselves wonders of quiet discipline. Imagine a detector so sensitive it can feel the impact of a single photon, a tiny packet of light. To work at this level, we must remove the noise of the everyday world. We cool our experiments to temperatures so low that the frantic dancing of atoms slows to a crawl. In this deep, artificial silence, the quantum whispers become audible. What we find is that nature, even in its most hidden corners, is not chaotic. It follows a different kind of logic, one that requires us to expand our definitions of what is real. In the quantum realm, a particle can behave like a wave, spreading out across space and interfering with itself. And yet, when we look for it, it appears as a particle again. This duality is not a contradiction, but a harmony we are just beginning to understand. It is a reminder that reality is far richer than our immediate senses would have us believe. As you listen, let the idea of a single, solid reality fade. Allow yourself to envision the universe as a vast field of overlapping possibilities, a quiet sea where waves of probability rise and fall in a slow, eternal rhythm. This introduction to the quantum landscape is meant to serve as a bridge. We are leaving behind the world of is and entering the world of might be. But as we do, notice that the world's reliability has not faded. Your house still stands, the stars still shine, and the laws of physics still hold. The quantum world is the foundation upon which the classical world is built. It is the secret architecture that allows everything else to exist. By understanding the softening of certainty, we are not losing our grip on truth. We are reaching for a deeper, more fundamental truth. It is a truth that requires patience and a willingness to let go of the familiar. Settle in now. Let the weight of your body be supported by the reliable structure of the world, even as your mind begins to drift into the fluid, beautiful depths of quantum reality. We are at the beginning of a long, quiet walk through the most fundamental layers of existence. There is no rush to reach the end. Each step is an opportunity to appreciate the subtle order governing the universe's smallest structures. The journey is slow, the path is quiet. And the destination is a deeper sense of wonder at the silent consistency of nature. Human intuition is a remarkable tool, but it is also deeply specialized. It was shaped slowly over hundreds of thousands of years to help small groups of humans survive in a narrow band of environments. It helps judge distance well enough to throw a stone. It estimates speed accurately enough to avoid a falling branch. It senses cause and effect clearly when one solid object strikes another. What it was never designed to do is describe the behavior of reality at scales far smaller than anything a human body can interact with directly. The brain builds its expectations from experience. From childhood onward, the world appears solid, continuous, and stable. Objects remain where they are unless something pushes them. Motion follows smooth paths. Causes precede effects in a tidy sequence. These patterns are reinforced millions of times over a lifetime until they feel not just familiar but inevitable. It is hardly surprising, then, that when physics reveals a domain where these expectations no longer hold, the reaction is discomfort rather than curiosity. At very small scales, intuition begins to mislead almost immediately. The idea that an object must always be somewhere specific feels obvious. Yet nature does not seem obligated to honor that expectation. The assumption that things move along clear trajectories works beautifully for planets and projectiles, but quietly fails for electrons and photons. This failure does not arise because the universe becomes chaotic or poorly behaved. It arises because intuition was never built to operate there in the first place. Evolutionary biology offers a useful lens here. Natural selection rewards traits that improve survival and reproduction, not traits that reveal fundamental truth. A mind that accurately predicts the motion of prey across a savanna has a clear advantage. A mind that understands probability distributions at atomic scales does not. As a result, the nervous system prioritizes speed, efficiency, and usefulness over precision or completeness. It compresses reality into simplified models that work well enough at human scale, and it discards the rest. Vision itself provides a simple example. Human eyes respond to a narrow slice of electromagnetic radiation, ignoring most of what exists. Hearing detects vibrations within a limited range, filtering out everything beyond it. Touch averages over countless microscopic interactions to produce the sensation of a smooth surface. None of these senses report reality as it truly is in detail. They report a practical summary. Quantum physics operates far below this summary in a region where the shortcuts taken by perception no longer apply. Because of this, quantum behavior feels strange, not because it is illogical, but because it refuses to conform to expectations that were never meant to describe it. When experiments show that outcomes can only be predicted probabilistically, this clashes with the deeply ingrained belief that the world must unfold in a single definite way. When particles behave like waves in some situations and like particles in others, it feels like a contradiction, even though it is a consistent description supported by repeated observation. Physics advances precisely by recognizing when intuition has reached its limit. History shows this pattern clearly. Classical mechanics once seemed complete, explaining the motion of objects from falling apples to orbiting planets. Yet, as measurements became more precise, small discrepancies appeared. These were not failures of experimentation, but signals that familiar concepts were being stretched beyond their domain of usefulness. In the early years of the 20th century, this tension became impossible to ignore. Experiments probing heat radiation, atomic structure, and the behavior of light produced results that simply refused to fit existing frameworks. Scientists trained in classical thinking found themselves facing data that demanded something new. The discomfort was not subtle. Many of the figures who would later become associated with quantum theory expressed open frustration with its implications. Confusion was not a sign of incompetence. It was the natural response of human intuition meeting a regime it was never built to navigate. What is often overlooked is how carefully this confusion was handled. Quantum theory did not emerge from speculation or philosophical preference. It emerged because experiments left no alternative. The specialization of the human mind means that we are often blind to the true nature of the medium we exist in. We are like creatures living in a two-dimensional world trying to fathom the concept of height. Our brains seek patterns that correlate with physical safety and resource acquisition. This is why the concept of solid feels so fundamental. To a prehistoric human, a rock was solid, and that fact was vital for survival. But the solidity we feel is merely a sensation created by the interaction of fields, a topic we will explore later. At the quantum level, the very notion of a thing occupying a place becomes an approximation that loses its meaning. To accept this, we must acknowledge that our brains are biased filters. We do not perceive the universe as it is. We perceive a curated, high-level summary designed for a medium-sized organism moving at medium speeds. This realization is actually quite liberating. It means that the strangeness of quantum mechanics is not a flaw in the theory, but a testament to how far we have traveled beyond our biological origins. We have used the tools of mathematics and technology to step outside the narrow corridor of our evolution. We are peering into the basement of reality using light our eyes cannot see and logic our instincts do not recognize. If we look at how children learn, we see the foundation of this rigid intuition. A child drops a toy and learns it falls down. They push a ball and see it roll. These experiences form the classical neural pathways. By the time we are adults, these pathways are like deep grooves in a record. Quantum mechanics requires us to lift the needle out of those grooves. It asks us to consider that the toy might not have a single path it takes to the floor, or that the ball might be in several places at once until someone catches it. This feels like nonsense because our survival depended on it being nonsense. If our ancestors had spent their time contemplating the wave functions of the predators stalking them, they would not have survived to pass on their genes. Therefore, our discomfort with quantum reality is a survival mechanism that has outlived its primary purpose. In the modern world, we can afford to be still. We can afford to quiet these instinctive protests. As you settle into this thought, let the tension of needing to understand according to your old rules slip away. You are more than just a biological survival machine. You are a witness to the deeper structures of the cosmos. Accepting the limits of intuition is the first step toward true clarity. It is an act of intellectual humility. We are admitting that the universe is not obligated to be sensible to a primate brain. Once this is accepted, the weirdness of quantum physics stops being a barrier and starts being a gateway. It allows us to approach the subject with a sense of wonder rather than frustration. We are no longer trying to force the atom to behave like a tiny billiard ball. We are allowing the atom to be whatever it truly is. This shift in mindset is like loosening a tight grip. As you relax your hold on how things should behave, you create space for how things actually do behave. The universe is a disciplined, orderly, and beautiful place, but its order is not the order of the savanna or the forest. It is an order of symmetry, probability, and fields. It is a quiet, profound structure that exists beneath every breath you take and every thought you have. By recognizing that your intuition is a specialized tool, you can put that tool aside for a moment and look through a different lens, one that reveals a world of subtle, shimmering potential. There is a common temptation to treat quantum physics as evidence that reality is fundamentally irrational. In truth, it is extraordinarily disciplined. Its predictions are among the most accurate ever produced by science. Devices built upon quantum principles operate with astonishing reliability, from the timing systems used in global navigation to the electronics that quietly manage modern life. Strangeness does not imply instability. It simply signals an unfamiliar structure. Accepting this requires a gentle adjustment of expectations. Instead of asking why quantum behavior does not make intuitive sense, it becomes more useful to ask why intuition should be trusted there at all. Just as eyesight cannot reveal ultraviolet light without assistance, intuition cannot reveal atomic behavior without guidance. Instruments extend the senses. Mathematics extends reasoning. Together they allow access to domains that would otherwise remain inaccessible. This process can feel unsettling at first, particularly when long-held assumptions are loosened. Yet, it is also deeply human. Science progresses by recognizing the limits of what feels obvious and allowing evidence to lead the way. Each time intuition falters, it opens space for a deeper understanding to form, one that is less tied to immediate experience and more closely aligned with how nature actually behaves. There is a quiet reassurance in this. The universe does not change its rules depending on whether they feel comfortable. It behaves consistently, patiently, and without regard for expectation. When intuition fails, it is not a sign that reality is broken. It is a reminder that understanding is a skill that must be extended, not a sense that arrives fully formed. By softening resistance early, it becomes possible to approach unfamiliar ideas without tension. Confusion no longer feels like a problem to be solved quickly, but a natural stage in learning something genuinely new. Discomfort fades, replaced by curiosity. And with curiosity comes the willingness to let evidence speak, even when it whispers something unexpected. From this perspective, the limits of human intuition are not obstacles. They are signposts. They mark the boundary where everyday experience ends and deeper structure begins. Beyond that boundary lies not chaos, but a quieter, subtler order, waiting to be understood on its own terms. To move beyond classical logic is to stop insisting that the universe be a series of simple mechanical gears and to start seeing it as a vast, interconnected field of possibilities. In the classical world, logic is binary. Something is here or there. A switch is either on or it is off. This either-or thinking is the bedrock of our daily lives, and it serves us well when we are navigating the macroscopic world. But as we move into the quantum domain, we find that nature employs a logic of both and or neither nor. A particle can exist in a superposition of states. occupying a range of possibilities simultaneously until a measurement is made. This does not mean the particle is confused or that the laws of physics have stopped working. It means that at its most fundamental level, reality is not built from distinct, isolated bits of information, but from a continuous fabric of potential. When we attempt to force this fluid reality into our rigid binary boxes, it appears strange. But if we learn to sit quietly with the strangeness, a new kind of clarity emerges. We begin to see that the strangeness is merely the shadow cast by a more expansive truth. The discipline of the strange is the practice of following the mathematics and the experiments even when they lead away from the familiar. It is the recognition that our mental models are just that, models, and that reality is far more generous than our imaginations. Consider the early pioneers of this field, like Max Planck and Albert Einstein. They did not set out to create a world of paradoxes. They were forced into it by the sheer weight of experimental evidence. Planck, a deeply conservative physicist, spent years trying to reconcile his findings with classical thermodynamics. He only introduced the idea of quanta as a last resort, a mathematical necessity that he hoped would eventually be replaced by something more traditional. It never was. Instead, that tiny seed of quantization grew into a forest that transformed our entire understanding of the cosmos. These scientists demonstrated a profound kind of bravery, the bravery to be wrong about the very nature of existence. They let the universe surprise them. As you listen to these words, try to adopt that same spirit of quiet openness. You do not need to solve the mystery of quantum mechanics tonight. You only need to enable it to exist. Let the rigid walls of your classical logic soften. Imagine the binary world of yes and no dissolving into a gentle shimmering perhaps. In this potential space, there is no room for anxiety or tension. There is only the slow, rhythmic unfolding of a deeper order. This transition from certain to probable is like learning to see in the dark. At first, you may feel lost, reaching out for the solid shapes you are used to, but as your eyes adjust, you begin to perceive a different kind of landscape. You see that the darkness is not empty. It is full of subtle structures and hidden symmetries. The discipline of the strange is the ability to trust this new way of seeing. It is the understanding that just because something cannot be visualized as a solid object doesn't mean it isn't real. In fact, many of the most real things in our lives, love, time, gravity, defy simple visualization. We accept them because we feel their effects. Quantum mechanics asks us to extend this same grace to the subatomic world. We may not be able to see a wave function, but we can see the results of its work in the technology we use and the very stability of the atoms that make up our bodies. There is a deep, quiet integrity to this way of thinking. It aligns us with the universe as it actually is, rather than how we wish it to be. As we conclude this reflection on moving beyond classical logic, notice the feeling of your breath. It is a slow, continuous cycle, a physical expression of the very rhythms that govern the quantum world. Just as your breath connects you to the air around you, the quantum fields connect you to the furthest reaches of the cosmos. We are never truly separate from the strangeness we are discussing. It is the very stuff of our being. By moving beyond the limits of our narrow classical intuition, we are not traveling to a foreign land. We are finally coming home to the true nature of the reality we have always inhabited. It is a home that is vast, quiet, and beautifully disciplined. It is a place where every outcome is a possibility and every interaction is a moment of creation. Settle deeper into this realization. Let the strange become familiar, and let the unintuitive become a source of comfort. The universe is consistent, it is reliable, and it is waiting for you to simply be present within its quiet, structured depths. Touch feels convincing. A table resists pressure, a stone carries weight, walls do their job reliably. From the moment hands can grasp objects, the world presents itself as firm and continuous, built from solid pieces pressed tightly together. This impression is reinforced every day so consistently that it rarely invites questions. Matter feels compact because it behaves that way at human scale. Yet when examined more closely, the confidence begins to dissolve. At the level of atoms, solidity fades into something far more delicate. An atom is not a miniature solid object packed tightly with material. It is mostly space, vast amounts of it relative to the tiny structures that define its presence. If an atom were enlarged to the size of a large cathedral, the central nucleus would be smaller than a grain of dust suspended at its center. The rest would be empty volume, lightly occupied by a diffuse region where electrons are likely to be found, but rarely pinned to a precise location. This idea runs directly against intuition. Empty space is usually associated with absence, with nothingness. Yet atoms, despite being mostly empty, combine to form materials that feel unquestionably solid. The key lies not in how much space they contain, but in how they interact. Forces, not bulk, do the heavy lifting. Early models of the atom did not begin with this picture. For much of the 19th century, atoms were imagined as indivisible units, solid and featureless. They were useful bookkeeping tools for chemistry, not objects with internal structure. This began to change as experimental techniques improved and questions became sharper. The assumption of indivisibility could not survive direct investigation. One of the most decisive moments came through experiments led by Ernest Rutherford in the early 1900s. By directing streams of charged particles toward thin sheets of gold foil, his team expected to see minor deflections consistent with a soft, spread-out distribution of charge. Most particles passed straight through as predicted, but a small fraction scattered sharply, some even rebounding backward. It was an outcome so unexpected that Rutherford famously likened it to firing a shell at tissue paper and having it bounce back. The implication was unavoidable. Atoms contained a tiny dense core where most of their mass and positive charge resided. This nucleus occupied only a minute fraction of the atom's volume, yet exerted enough influence to dramatically redirect incoming particles. The rest of the atom had to be largely empty, offering little resistance. This discovery dismantled the idea of atoms as compact solids. It replaced it with a structure that was mostly absent, punctuated by a concentrated center. The result was not a philosophical speculation, but a conclusion demanded by experimental evidence. Matter, it turned out, was already stranger than it appeared. Imagine yourself standing in the center of that metaphorical cathedral. The air around you is still and silent. You are surrounded by vast, towering reaches of space, seemingly empty and void of substance. Yet, this space is the very foundation of everything you have ever touched. The grain of dust at the center, the nucleus, holds the overwhelming majority of the matter, while the electrons exist as a ghostly, shimmering presence throughout the rest of the volume. This architecture is not one of bricks and mortar, but one of fields and probabilities. We often think of empty as meaning nothing, but in the heart of the atom, emptiness is the stage upon which the most fundamental forces of nature perform. It is a structured emptiness, a disciplined void that maintains its shape with a consistency that puts the strongest steel to shame. When you sit in a chair, you are not resting on solid matter. You are being supported by the invisible, powerful repulsion of electron clouds, resisting one another across this vast atomic space. There is a profound, quiet elegance to the fact that the most solid things in our lives are built upon a foundation of nearly absolute nothingness. As we peer deeper into this emptiness, we must let go of our desire for little balls orbiting a sun. Niels Bohr extended the emerging picture of the atom by proposing a model in which electrons occupied specific regions around the nucleus associated with particular energies. While later refinements would replace simple orbital paths with probability distributions, Bohr's work provided a crucial stepping stone. It showed that atomic structure followed rules that were precise, constrained, and deeply unfamiliar to classical thinking. What is striking is how quickly this strange architecture proved reliable. Atomic models, once adjusted to reflect experimental reality, began to explain chemical behavior with remarkable accuracy. The periodic table gained deeper meaning. Spectral lines, once mysterious, became signatures of atomic structure. The emptiness within atoms did not make matter unstable, it made it understandable. It revealed that the universe is not a collection of solid marbles, but a delicate, vibrating web of energy and space. Each atom is a tiny pocket of order in the vastness, a place where the void has been organized into a stable, enduring pattern. There is a quiet, meditative quality to contemplating this atomic architecture. Think of the sheer number of these empty cathedrals that make up your own body. Trillions upon trillions of them, each one mostly space, yet each one perfectly coordinated with its neighbors to create the sensation of a solid, breathing being. You are, in a real sense, a ghost made of light and empty space, held together by the silent persistence of physical law. This realization doesn't make you less real. It makes the fact of your existence more miraculous. It shifts the focus from what we are made of to how we are organized. The beauty of the universe lies not in the stuff it contains, but in the intricate, subtle ways that nothing is woven into something. As you drift into sleep, let the image of these vast, quiet atomic spaces fill your mind. See them as calm, light-filled chambers where everything is in balance. The nucleus at the center, the electron clouds at the edges, and the beautiful structured emptiness in between. The lesson of the atom is that appearances are merely the surface of a much deeper ocean. We see solidity, but nature knows space. We see boundaries, but nature knows forces. By peering inside the atom, we are training our minds to look past the obvious and to appreciate the subtle. We are learning that stability does not require density, nor does strength require bulk. The universe is a master of economy, using the smallest amount of matter to create the greatest amount of structure. This same economy can be found in the way your mind settles as it moves away from the clutter of the day. Just as the atom finds its stability in the vastness of its interior space, you can find your own peace by leaning into the quiet, open reaches of your own consciousness. Let the solid world dissolve. Let the Om Cathedral be your sanctuary. There is no weight here, only balance, no pressure, only presence. The architecture of emptiness is the quietest, most reliable home we could ever ask for. It is a home that exists within us and around us, silently doing its work, ensuring that the world remains stable while we dream. So why do solids feel solid? The answer lies in interaction rather than occupancy. Electrons in one atom resist being pushed into the same states as electrons in another. Electromagnetic forces create strong repulsion at close distances. When a hand presses against a table, the sensation arises not because atoms touch like billiard balls, but because the electron clouds surrounding atoms resist compression. What feels like contact is actually a balance of forces. In this sense, solidity is an emergent sensation. It arises from countless interactions governed by underlying rules, not from material being packed edge to edge. The same principle explains why a metal bar supports weight while air does not. Despite both being composed of atoms that are mostly empty, structure, arrangement, and interaction matter far more than density alone. There is a subtle comfort in this realization. The world does not lose credibility when examined closely. Chairs remain dependable. Floors continue to hold. The emptiness within atoms does not undermine everyday experience. It simply reveals that experience is built atop deeper mechanisms quietly doing their work without demanding attention. This perspective also serves as a concrete example of intuition meeting its limits at human scale. Assuming solidity works perfectly well at the macroscopic scale, but at the atomic scale it misleads. Neither view is wrong within its proper domain. Problems arise only when one is stretched beyond where it applies. Recognizing this makes it easier to accept that familiar concepts may need adjustment without being discarded entirely. There is gentle humor in how misleading appearances can be. A seemingly solid wall turns out to be a delicate arrangement of mostly empty atoms held together by invisible forces behaving with unwavering consistency. It is not the sort of emptiness associated with fragility or collapse. It is structured emptiness, disciplined and reliable. Scientific bodies and laboratories around the world continue to refine this understanding, using increasingly precise instruments to probe atomic and subatomic structure. Particle accelerators, spectroscopy, and imaging techniques all confirm the same basic picture. Matter is stable not because it is filled, but because it is governed. By confronting the emptiness at the heart of matter, a deeper lesson quietly takes shape. Reality does not need to conform to how it appears to function beautifully. Consider the feeling of sitting back in your chair listening to these words. Your body is composed of trillions of atoms, and the chair is composed of trillions more. As you settle your weight, the atoms of your clothing and skin come close to the atoms of the chair's surface. In the classical mind, we imagine two solid surfaces meeting. But in quantum reality, something much more rhythmic and invisible is happening. The electrons orbiting the nuclei in your body are approaching the electrons in the chair. Because electrons carry a negative charge, and like charges repel one another, they push back. They do not want to overlap. This pushing back is the solidity you feel. It is a silent, microscopic dance of avoidance. If these forces were to vanish for even a microsecond, you would fall straight through the chair, through the floor, and toward the center of the earth. We live our lives supported by a shimmering, invisible cushion of electromagnetic repulsion. This force is so strong and so consistent that it creates the illusion of a continuous hard surface. It is a testament to the power of the invisible. We trust the floor, not because it is full, but because the laws of physics are relentless in their enforcement of this balance. The assumption that matter must be compact and solid dissolves under scrutiny, replaced by a subtler and more elegant framework. It is one where space, force, and probability combine to produce the familiar world without ever quite becoming what intuition expects. Seen this way, the limits of intuition are no longer abstract, they are tangible. A solid object resting calmly in a room becomes a reminder that understanding deepens not by clinging to appearances, but by allowing evidence to reshape expectation. And once that reshaping begins, the strange quickly becomes coherent, even reassuring on its own quiet terms. Imagine the world as a vast, interconnected web of these forces. Every object you see is a localized knot of electromagnetic tension. The mountain is a massive accumulation of these atomic repulsions. The feather is a light, delicate arrangement of the same. The difference is only in the pattern, not the underlying principle. There is no stuff that is inherently hard or soft. There are only arrangements of force that respond to our touch in different ways. This realization allows a profound softening of the mind. If the world is not made of hard, cold blocks, but of dynamic, responsive forces, then the barrier between us and the world becomes a bit more fluid. We are part of the same field of interaction. Our atoms are dancing to the same music as the atoms of the air and the atoms of the stars. The sensation of being a solid, isolated entity is a useful shortcut for our daily survival. But in the quiet of the night, we can acknowledge the truth. We are integrated into a continuous tapestry of energy. There is no place where you truly end and the chair truly begins in terms of a hard boundary. There is only a region where the forces of repulsion become strong enough to be felt. This connectivity is a source of great peace. You are not a lonely object in a void. You are a participant in a universal field of balanced interactions. Everything is held in place by a quiet, unwavering discipline that began at the dawn of time and continues in every atom of your being. As you drift closer to sleep, let the feeling of solidity transform into a feeling of support. You are being held by the universe itself. Every atom of the bed beneath you is doing its part, pushing back with perfect precision to keep you safe and cradled. You do not need to do anything to maintain this. The forces are automatic. They are tireless. They are the silent sentinels of your physical existence. Let the tension in your muscles dissolve, knowing that you are supported by an invisible quantum architecture that never sleeps. The world feels solid because it is governed by love for order and consistency. It is a reliable stage for the drama of life, built from the most delicate of materials, space and light. Settle into this quiet, supported state. Let the weight of the day be carried by the relentless repulsion of electron clouds. You are safe, you are held, and you are part of a beautifully balanced reality that functions perfectly, even when you aren't looking. The stillness you feel now is the same stillness that resides at the heart of every atom, a stillness born of perfect balance and unwavering law. Energy feels smooth. A dimmer switch brightens a room gradually. A fire cools slowly as embers fade. Warmth seems to flow, not arrive in steps. This impression fits comfortably with everyday experience. CE, where change appears continuous and divisible without limit. For a long time, physics assumed the same. Energy, it was thought, could be added or removed in any amount, however small. Nature, it seemed, had no preference for neat divisions. That assumption worked remarkably well for many problems. Classical physics described motion, heat, and light with impressive accuracy across a wide range of situations. Yet, as measurements grew more precise toward the end of the 19th century, cracks began to appear. Certain experiments refused to behave as expected, no matter how carefully the calculations were adjusted. The smooth picture of energy began to fray at the edges. One of the most stubborn problems involved something deceptively ordinary: glowing objects. Any warm material emits light. As temperature rises, the color and intensity of that glow change in predictable ways. This phenomenon, known as blackbody radiation, should have been straightforward to explain. Classical theories predicted how much energy should be emitted at different colors, assuming energy flowed continuously. They were wrong, spectacularly so. According to classical predictions, a hot object should emit infinite energy at high frequencies, producing an ever-increasing amount of ultraviolet light. This outcome, later nicknamed the ultraviolet catastrophe, was not a minor discrepancy. It was a complete failure of the logic that had governed science for centuries. Real objects simply did not behave this way. Measurements showed that emitted energy rose to a peak and then declined smoothly without any runaway explosion of ultraviolet radiation. The problem was not an experimental error. Laboratories across Europe reproduced the same curves again and again. The failure lay in the underlying assumptions of continuity. Something about the way energy was being treated as a smooth, endless fluid simply did not match the reality of the microscopic world. In 1900, Max Planck approached the problem with deep reluctance. He did not set out to overturn physics. His goal was merely to find a mathematical description that fit the data. To do so, he introduced an idea he regarded as a formal trick, rather than a statement about nature. He proposed that energy could only be exchanged in discrete amounts proportional to the frequency of radiation. Instead of flowing smoothly, energy arrived in packets. At first, this proposal felt absurd. Even to its author, there was no intuitive reason energy should behave this way. Nothing in everyday experience suggested it. Planck himself hoped the assumption could later be discarded, leaving the equations intact. But the equations worked precisely because of that assumption, and without it, they failed entirely. This marked the quiet birth of quantization. Energy, it seemed, was not infinitely divisible. It came in fixed units, now known as quanta. These units were not arbitrary. Their size was set by a constant of nature, a number so small that TS effects only become noticeable at microscopic scales. At the human scale, the steps are tiny enough to appear smooth, much like individual grains of sand blending into a continuous beach. The significance of this shift is difficult to overstate. Quantization was not an interpretation layered onto existing theory. It was a structural rule forced into place by experimental evidence. The universe itself appeared to insist on it. Once introduced, the idea began to solve problems that had resisted explanation for years. Blackbody radiation curves matched observations perfectly. Heat capacity measurements at low temperatures began to make sense. The strange behavior of light and matter at small scales started to form a coherent pattern. What is striking is how conservative this revolution was. Planck did not announce a new worldview. He followed the data where it led, even when it led somewhere uncomfortable. Quantization arose from necessity, not imagination. It was a reluctant conclusion accepted because no alternative survived contact with experiment. This reluctance extended beyond Planck. Many physicists initially viewed quantization as a temporary patch, a clever fix awaiting a deeper, more classical explanation. Yet, as time passed, the pattern repeated. Whenever classical assumptions of smoothness were applied to atomic-scale systems, predictions failed. Whenever energy was treated as coming in discrete amounts, predictions succeeded. Nature was consistent, even if the implications were unsettling to the classical mind. The idea of fixed energy exchanges deepened the departure from classical expectations already underway. Matter was no longer solid in the traditional sense, and now energy itself refused to behave as a smooth substance. Both insights pointed in the same direction. The familiar concepts that worked so well at large scales were becoming unreliable guides at small ones. There is a subtle elegance in this departure from smoothness. Quantization introduces order, not chaos. By limiting the allowed energy values, it creates structure. Atomic stability depends on it. Without quantized energy levels, electrons would spiral unpredictably. Atoms would collapse, and chemistry would dissolve into noise. The universe, as it turns out, relies on these tiny, discrete steps to remain coherent. There is a gentle humor in how unintuitive this feels. A warm object does not emit heat in an endless drizzle, but in a disciplined sequence of microscopic drops. The steps are simply too small to notice without sensitive instruments. What seems continuous is often only continuous by approximation. Imagine walking across a floor that feels perfectly flat, only to discover under a microscope that it is made of trillions of tiny individual tiles. The smoothness was merely a trick of distance. As we approach the heart of reality, the tiles become visible. We find that nature is not a blurry smear, but a sharply defined mosaic. This realization does not make the world less beautiful, it makes it more intricate. Scientific institutions and laboratories worldwide have confirmed quantization through countless experiments. Spectroscopy reveals discrete lines where continuous bands are expected. Precision measurements of light and heat align perfectly with quantized models. Technology built upon these principles functions reliably every day, rarely drawing attention to the strange rules beneath its operation. Accepting quantization requires the same adjustment of intuition encountered before. Energy does not owe reality to familiarity. It follows its own rules, indifferent to whether they feel natural to us. Once this is accepted, the confusion fades. What remains is a quieter appreciation for how deeply structured the universe is, even where it appears most smooth. Quantization stands as the first unmistakable signal that classical expectations have reached their limit. It is the point where continuity gives way to discreteness, not as a philosophical statement, but as an experimentally enforced fact. From this foundation, the deeper architecture of quantum reality begins to take shape, one small step at a time. As you drift toward rest, imagine the energy in the room not as a chaotic flood, but as a gentle, organized rain of tiny packets, falling in perfect rhythm, maintaining the quiet order of the night. The shift from a world of infinite smoothness to a world of discrete packets was perhaps the most profound adjustment in the history of human thought. It required a departure from the calculus of the continuous that had defined science since the time of Isaac Newton. In that older view, you could always divide a distance in half, and then half again forever. You could always turn down a flame just a little bit more, without ever reaching a final indivisible drop of heat. But the birth of quantization revealed that nature has a flaw. It has a minimum set of denominations, much like a currency that has a smallest coin. You can have one coin, or two, or three, but you can never have 1.5. This realization was not just a mathematical curiosity, it was a statement about the very grain of the universe. If you were to zoom in deep enough on the flow of time, the movement of light, or the vibration of an atom, you would eventually find that the smooth motion we perceive is actually a series of tiny discrete jumps. The universe does not glide, it stutters, but it does so with such incredible speed and on such a minute scale that the transitions are invisible to the naked eye. Max Planck's discovery of the constant that bears his name, Planck's constant, provided the scale for these packets. This number, denoted ash, is unimaginably small, roughly 6.626 times 10^-34 joule seconds. Because it is so small, the graininess of reality is hidden from us in our daily lives. When you throw a ball, the energy it carries is technically quantized, but the steps between one energy level and t. He next are so close together that the ball's flight appears perfectly smooth. It is only when we look at the scale of an individual atom that these steps become wide chasms. An electron in an atom cannot simply sit anywhere it likes. It is confined to specific stairs of energy. To move from one stair to the next, it must disappear from one and instantaneously reappear on the other without ever passing through the space in between. This is the famous quantum leap. It is a concept that defies our logic of motion, yet it is the only way to explain why atoms do not simply collapse. By forcing energy into these discrete packets, or quanta, nature ensures that the universe is not a blurry smear, but a collection of distinct stable states. This idea of quantization extends to light itself, a concept that Albert Einstein took further 5 years after Planck's initial work. While Planck thought quantization was just a quirk of how matter absorbed and emitted energy, Einstein proposed that light itself was made of these packets. He called them light quanta, which we now know as photons. Imagine a beam of light not as a continuous wave of water, but as a stream of tiny energetic hail. Each hailstone of light carries a specific amount of energy determined by its color. Blue light has larger packets, red light has smaller ones. This was the key to solving the photoelectric effect, showing that no matter how much red light you shine on a piece of metal, you might never knock an electron loose, because each individual red packet is too weak, but a single blue packet, being larger and more energetic, can do the job instantly. This proved that quantization was not a mathematical trick, but a physical reality. Light, the very thing that seems most fluid and ethereal, is actually made of countable discrete bits. The birth of quantization also brought a new rhythm to the way we describe the cosmos. In a continuous world, anything is possible, and everything is a bit vague. In a quantized world, there is a deep sense of rightness and precision. Things are in one state or another. This discreteness is what enables the digital world we live in today. Computers, at their heart, are machines of discrete states, ones and zeros. This digital nature is a direct reflection of the underlying quantum reality. If energy and information were truly continuous, our modern electronics would likely be impossible, as the subtle drifts in energy would eventually wash away the data. But because the universe is quantized, we can build systems that rely on the absolute distinction between one packet of energy and none. There is a quiet structural integrity to a universe built this way. It is like a building made of sturdy individual bricks rather than one molded from wet clay. Each piece has its place, and the whole is stable because the parts are definite. As we ponder these packets of reality, let the idea of smoothness gently dissolve from your mind. Think of the light in the room as a soft rain of photons, each one hitting with a tiny, discrete impact. Think of the heat in your skin as the vibration of atoms, each vibrating at a specific, allowed frequency. There is no chaos here, only a very fine-grained order. The universe is like a masterpiece of pointillism, where trillions of tiny dots come together to form a beautiful, coherent image. From afar, the dots fade, and we see a world of smooth curves and gradual changes. But as we rest in the quiet of the night, we can acknowledge the dots. We can appreciate the quanta that make up our existence. This realization brings a sense of clarity. The world is not slipping our fingers. It is built on a foundation of solid, countable truths. Each packet of energy is a tiny, reliable pulse of existence, governed by a constant that has remained unchanged since the beginning of time. There is a profound comfort in the idea of a quantized universe. It means that there is a limit to how small things can get, and a limit to how much noise the universe can produce. By setting a minimum scale, nature creates a threshold for stability. It prevents the infinite runaway problems that classical physics predicted, like the ultraviolet catastrophe. The packets are like the safety valves of reality, ensuring that energy stays contained and organized. As you drift towards sleep, imagine yourself as part of this quantized rhythm. your breath, your heartbeat, the very thoughts moving through your mind. Ow! All of them are supported by these microscopic, discrete steps. You are a coherent whole made of 1,000,000,000,000 tiny stable parts. The graininess of the universe is not a distraction. It is the very thing that allows you to be you. Settle into the quiet, rhythmic pulses of your own being. Let the discrete nature of the quantum world act as a lullaby, a steady tick-tick-tick of existence that never fails and never falters. The steps are small, the packets are light, and the structure is absolute. Light feels familiar. It illuminates rooms, warms skin, and reflects softly from surfaces without drawing attention to itself. For centuries, it was treated as a wave spreading smoothly through space like ripples across water. This description worked beautifully. It explained reflection, refraction, interference, and diffraction with elegant precision. By the late 19th century, the wave theory of light was one of the great successes of classical physics. And yet, even as confidence grew, small experimental details began to whisper that something was missing. Waves, as they were understood, carried energy continuously. Increase the brightness, and more energy should arrive. Lower the brightness, and less should follow. Color or frequency should not fundamentally change how energy is delivered, only how it is distributed. These expectations seemed reasonable, grounded in experience and supported by mathematics. But when light interacted with matter at very small scales, those expectations quietly collapsed. One of the clearest examples came from experiments involving metal surfaces exposed to light. When certain metals were illuminated, electrons were ejected from their surface. This phenomenon, later called the photoelectric effect, had been observed before, but careful measurements revealed something deeply puzzling. The energy of the ejected electrons did not depend on how bright the light was. Instead, it depended on the color. Below a certain frequency, no electrons were released at all, no matter how intense the light became. Increase the brightness as much as you like and nothing happens. But raise the frequency just beyond a specific threshold and electrons were ejected instantly. Even when the light was faint, there was no gradual build-up, no delay. The effect appeared immediately. This behavior made no sense within a purely wave-based description. If energy arrived continuously, brighter light should eventually free electrons regardless of color. Experiments showed otherwise. The results were consistent, reproducible, and stubbornly resistant to classical explanation. In 1905, Albert Einstein provided a crucial insight. Building directly on the idea of energy quantization, he proposed that light sometimes behaves as if it arrives in discrete packets, each carrying a specific amount of energy tied to its frequency. If a single packet carried enough energy, it could eject an electron. If it did not, no amount of additional light would help because the energy was not pooled. It arrived one packet at a time. This was not a philosophical claim about the nature of light. It was a physical explanation for observed behavior, and it worked. The photoelectric effect followed naturally once light was treated as particulate in this specific context. What made this proposal so unsettling was not that light behaved like a particle, but that it did so only under certain conditions. In other experiments, light continued to display unmistakable wave-like behavior. Interference patterns appeared, diffraction spread beams into fringes, reflection and refraction remained perfectly wave-like. There was no single description that fit all situations at once. This was not indecision on nature's part, it was another kind of consistency. The behavior of light depended on how it was interacting with the world. When spreading freely or passing through slits, wave descriptions captured its behavior precisely. When exchanging energy with matter at small scales, particle-like descriptions became unavoidable. The same entity obeyed different rules depending on the context of interaction. This is often described as wave-particle duality, though the phrase can be misleading. It suggests that light switches identities as if choosing between costumes. In reality, neither description is complete on its own. Waves and particles are human concepts borrowed from familiar experience. Light does not commit to either. It simply behaves as experiments show it does. The photoelectric effect was not the only evidence pointing in this direction, but it was among the most decisive. It demonstrated that energy quantization was not limited to abstract radiation models. It applied directly to physical interactions. Light could deliver energy only in discrete amounts, and matter responded accordingly. Einstein himself viewed this as a provisional step, rather than a final picture. He recognized its necessity even while remaining uneasy with the broader implications that would follow. His contribution confirmed that quantization was not confined to theoretical convenience. It was embedded in how light and matter actually behave. This shift carried a deeper message. Classical categories were beginning to fail. Waves and particles, long treated as distinct kinds of objects, were no longer sufficient as fundamental descriptions. They remained useful approximations, but they could not be applied universally without contradiction. The lesson here is subtle but profound. Behavior is not an intrinsic label attached to an object. It emerges from interaction. Light does not carry a fixed identity independent of circumstance. It reveals different aspects depending on what is being measured and how the measurement is arranged. There is a quiet elegance in this idea. Nature is not inconsistent. Human language is. The trouble arises when descriptions developed for one domain are forced onto another where they no longer apply cleanly. When that happens, confusion follows, not because reality is broken, but because expectations are misaligned. This understanding also builds naturally from energy quantization. If energy is exchanged in discrete amounts, then interactions must be described in ways that account for that discreteness. Waves alone cannot do this. Particles alone cannot capture interference. The deeper framework must accommodate both without reducing either to metaphor. Gentle humor often helps soften this transition. Light, it seems, refuses to settle into a single role. It behaves impeccably, just not according to the categories we would prefer. Like a guest who follows every rule of the house while ignoring the seating plan, it remains polite but unpredictable to the host. What matters is not how strange this feels, but how reliable it proves to be. Predictions based on this dual behavior match experiments with extraordinary accuracy. Technologies that depend on light interacting with matter, from imaging systems to sensors, rely on these principles every day without incident. The rules may feel counterintuitive, but they are remarkably reliable. Scientific institutions worldwide have tested and retested these ideas under countless conditions. The results remain consistent. Light does not misbehave. It simply does not conform to classical categories when those categories are applied too broadly. By accepting that behavior depends on interaction, a great deal of tension dissolves. The need to force light into a sin. Geo identity fades. What remains is a clearer view of how nature operates at small scales, guided by quantization and shaped by context. This marks another step away from classical expectations. Matter is not solid in the way it appears. Energy does not flow continuously, and light, perhaps most strikingly of all, refuses to be only one thing. It follows rules that are precise, experimentally grounded, and quietly indifferent to how comfortable they feel. Imagine a beam of light as a stream of possibilities. When it travels through the vastness of space, it spreads like a wave, exploring all paths at once. But the moment it strikes a surface or enters a detector, it chooses to manifest as a single discrete packet. This isn't a conscious choice, but a requirement of the interaction. It is as if light is a traveler who speaks many languages, choosing the one that is spoken in the land they are currently visiting. In the quiet of the night, we can appreciate this versatility. We are not forced to pick a side. We can simply witness the beautiful dual nature of the universe. The peace of this realization comes from the fact that light is reliable even in its complexity. You can trust the sunrise to be both a wave that fills the sky and a collection of photons that provide energy to the earth. You can trust the stars to be both a distant frequency and a physical impact on a telescope sensor. The refusal of light to be one thing is not a sign of chaos, but a sign of a deeper richness in the fabric of existence. As you drift towards sleep, let the duality of light serve as a reminder that we too are complex beings. We are not just one thing, we are a collection of many identities and possibilities, manifesting differently depending on where we are and who we are with. Like light, we are integrated into a system that is vast, precise, and infinitely nuanced. Settle into the quiet, shimmering potential of the dual guest. The waves are calm, the particles are steady, and the light is always, predictably, itself. In the classical world, we assume that objects possess intrinsic properties that belong to them, regardless of whether they're being watched or measured. A stone is heavy, a ball is red, and a mountain is tall. These attributes feel like permanent labels, fixed firmly to the identity of the object. We carry this logic into our everyday lives, believing that the world is a collection of things with traits that exist independently of our presence. However, as we descend into the quantum realm, this fundamental assumption begins to dissolve. We find that behavior is not a fixed label, it is a response. At these microscopic scales, identity is not something a particle has, it is something that emerges through interaction. A photon or an electron does not decide to be a wave or a particle in isolation. Instead, it manifests one aspect or the other, based entirely on the context of the experiment. This realization shifts our understanding of reality from a collection of static objects to a dynamic web of relationships. It suggests that at the most fundamental level, the universe is not made of stuff, but of events. This shift in perspective is profound because it challenges the very way we define existence. If an object's behavior changes based on how we look at it, then the act of looking is no longer a passive observation, it is a creative participation. In quantum mechanics, context is everything. Imagine a guest at a formal dinner who speaks with refined elegance, but then becomes boisterous and casual at a sporting event. We do not say the guest is inconsistent or that they have lost their identity. We recognize that different environments draw out different facets of their personality. Quantum entities behave in much the same way. When light passes through a narrow slit, the context of the environment emphasizes its wave-like nature, and it spreads out in beautiful interference patterns. But when that same light strikes a photographic plate, the context of the interaction demands a localized exchange of energy, and it manifests as a discrete particle. The identity of the light is not wave or particle, its identity is the potential to be either, depending on the conversation it is having with the rest of the universe. The history of physics in the 20th century is, in many ways, the story of scientists learning to accept this relational view of reality. Early researchers were deeply troubled by the idea that a single entity could exhibit contradictory behaviors. They searched for hidden variables, internal mechanisms that would explain why a particle chose one path over another. They wanted to believe that beneath the surface, there was a hidden truth that remained classical and certain, but as experiments became more sophisticated, it became clear that there was no hidden machinery. The truth was simply that properties are not local to the object. They are properties of the entire system, including the measuring device and the environment. This means that we cannot speak of an electron's position or momentum in a vacuum. We can only speak of how it responds to a specific measurement of position or a specific measurement of momentum. Identity is not stored inside the particle like a piece of data. It is a shared state that exists between the particle and its surroundings. There is a quiet, meditative beauty in this concept of contextual identity. It suggests that the universe is far more integrated than our senses suggest. If properties only emerge through interactions, then nothing truly exists in total isolation. Everything is waiting for a partner to interact with so that its qualities can be expressed. This perspective removes the coldness often associated with a materialistic view of the world. Instead of a universe of lonely, colliding marbles, we find a universe of endless dialogue. Every atom in your body is in a constant state of becoming, manifesting its properties through its relationships with the atoms nearby and the fields that permeate space. In the stillness of the night, you can sense this connectivity. You are not a solitary object drifting through a void. You are a focal point of countless interactions, each one contributing to the identity you experience as self. By letting go of the need for fixed internal labels, we open ourselves to the fluid and responsive nature of the cosmos. This understanding also helps mitigate the confusion surrounding the strangeness of quantum mechanics. The strangeness only appears when we try to force an object to have a single, context-free identity. When we stop asking, is light a wave or a particle, and start asking, how does light behave in this specific situation, the contradictions vanish. We begin to see that nature is being perfectly consistent. It is simply that its consistency is found in the rules of interaction rather than in the labels of objects. This requires a certain intellectual patience. It asks us to sit with the ambiguity of potential and wait for the interaction to reveal the result. In our daily lives, we are often rushed, seeking quick answers and firm definitions, but the quantum world invites us to move slower. It reminds us that reality is a process, and that who or what something is can only be understood in the context of the whole. As you settle further into the quiet of this exploration, consider how this applies to your own sense of being. We often feel pressure to be one thing, to have a fixed personality or a single path. But like the quantum world, we are collections of potential. We manifest different strengths, different memories, and different emotions, depending on the context of our lives. When we are in nature, we are one version of ourselves. When we are with loved ones, we are another. This isn't a lack of authenticity, it is the richness of a relational existence. We are both and, rather than either or. By embracing the quantum lesson of context, we can find a deeper peace with our own complexity. We can allow ourselves to be fluid and responsive, knowing that our identity is not a rigid cage, but a shimmering, ever-changing dance with the world around us. The reliability of the universe is not found in the permanence of objects, but in the consistency of relationships. We can trust that under the same conditions, nature will respond the same way. This is what makes science possible and technology dependable. The rules of the conversation are absolute, even if the speakers are versatile. As you drift towards sleep, let the idea of fixed, heavy identities fall away. Imagine yourself as a wave of potential, resting in a field of quiet interactions. There is no need to be this or there now. You can simply be the potential for rest, the potential for dreams, and the potential for a new manifestation in the light of the morning. The context of the night is silence and stillness, and in this context, your identity is one of deep, shimmering peace. Settle into the vast relational web of the cosmos, where every interaction is a whisper of order, and every moment is a shared expression of existence. Certainty feels reassuring. Drop a ball and it falls. Release a stone and it lands where expected. For centuries, physics reflected this comfort. Given enough information, the future could be calculated precisely. Positions led to velocities, velocities to trajectories, and trajectories to outcomes. The universe appeared to unfold like clockwork, each moment determined by the one before it. Quantum mechanics quietly breaks that expectation. At very small scales, even perfect knowledge of a system does not allow the prediction of a single definite outcome. Instead, it provides a range of possible results, each with a specific likelihood. Ask where a particle will be detected, and the answer is not a point but a distribution. Ask when an atom will emit light, and the response is not a schedule but a probability. This is not a measurement limitation, it is how the theory itself is structured. This shift can feel deeply unsettling at first. Probability is often associated with ignorance. A coin toss is uncertain because the details of motion are too complex to follow. Weather forecasts rely on probability because the atmosphere is chaotic. In these cases, probability stands in for missing information. If everything were known, certainty would return. Quantum mechanics does not work that way. Even in carefully controlled experiments, repeated under identical conditions, outcomes vary. The same preparation leads to different results. Not because something was overlooked, but because variation is built into the fabric of the description. The theory does not say what will happen. It says what can happen and how likely each possibility is. This idea took time to settle into its modern form. Early formulations of quantum mechanics produced mathematical objects that behaved like waves spreading through space and evolving smoothly over time. What those waves represented, however, was not immediately clear. They did not describe physical ripples like water waves. They were something else entirely. In the mid-1920s, Max Born offered a crucial interpretation. He proposed that these wave-like quantities did not represent matter itself but probability. Specifically, they described the likelihood of finding a particle in a particular place if a measurement were made. The wave did not tell where the particle was. It told where the particle might be found. This was a profound conceptual step. It reframed the entire theory. The maths remained unchanged, but its meaning shifted. The smooth evolution of the wave described how probabilities evolved over time. When a measurement occurred, a single outcome appeared, selected from the range of possibilities according to those probabilities. Born's proposal was not a philosophical decoration. It made direct contact with the experiment. When physicists measured the distribution of particles hitting a screen, the results matched the predicted probability patterns with remarkable accuracy. Individual events were unpredictable. Large numbers of events produce stable, repeatable distributions. This distinction matters. Quantum probability is not vague or approximate. It is precise. Experiments involving electrons, photons, and atoms confirm predicted probabilities again and again, often to extraordinary levels of precision. When millions of particles are measured, the statistical patterns align perfectly with theoretical expectations. Uncertainty remains at the level of individual outcomes, not at the level of the overall structure. This precision is one reason probability in quantum mechanics should not be confused with randomness. Randomness implies a lack of pattern. Quantum systems display strong, reliable patterns even while individual results remain unpredictable. The uncertainty lies not in the distribution, but in which member of that distribution will appear next. A helpful way to think about this is to reverse the usual intuition. In classical physics, certainty comes first and probability enters only when information is incomplete. In quantum physics, probability comes first and certainty appears only when many events are considered together. The order is inverted. This inversion reframes earlier ideas about wave and particle behavior. When light produces an interference pattern, it does so statistically. Individual photons arrive as discrete events, each striking a single point on a detector. Over time, a pattern emerges, not because each photon spreads out like a wave, but because the probabilities governing their arrival form a wave-like distribution. Seen this way, wave-particle duality becomes less puzzling. There is no need to imagine a single object switching identities. The wave describes probabilities, the particle describes outcomes. Both are essential and neither alone tells the full story. This perspective also explains why quantum mechanics resists deterministic interpretation. The theory does not lack information about hidden variables waiting to be uncovered. Extensive experimental tests have shown that attempts to restore classical determinism fail. The probabilistic structure appears to be fundamental, not provisional. This was one of the hardest aspects of quantum theory for many early physicists to accept. Albert Einstein famously objected to the idea that nature might be governed by chance, insisting that something deeper must be at work. R.S. shared his discomfort. Determinism had been a guiding principle for centuries, woven tightly into the identity of physics itself. Yet the evidence continued to point in the same direction. Experiments refined over decades supported Born's interpretation. Probability was not fading with improved measurement. It remained stubbornly central no matter how carefully systems were prepared or how sensitive instruments became. There is a quiet elegance to this outcome. Probability does not weaken the predictive power of quantum mechanics. It defines it. The theory tells exactly how often each outcome will occur, even if it cannot say which one will occur next. In many applications, this is more than sufficient. Lasers, semiconductors, and atomic clocks all rely on quantum probabilities behaving exactly as predicted. Scientific institutions and laboratories around the world test these predictions daily, often without drawing attention to the deeper implications. Devices work because probabilities behave reliably. Engineers design systems confident that statistical outcomes will align with theory, and they do. Accepting probability as fundamental requires a gentle shift in expectation. The universe is not a machine that reveals its future one inevitable step at a time. It is a system that offers possibilities constrained by precise rules and realized through interaction. Outcomes are not arbitrary. They are selected from a structured landscape of likelihood. There is even some kindness in this. Absolute determinism leaves no room for variation. Probability introduces flexibility without chaos. It allows systems to be stable on average while remaining open in detail. At small scales, this openness appears unavoidable. Gentle humor helps here as well. Nature, it seems, prefers to hedge its bets. It does not commit to a single outcome until asked, and even then, it follows a carefully weighted script rather than a rigid plan. The surprise is not that certainty disappears, but that so much order remains. By reframing wave-particle behavior in statistical terms, probability brings coherence where confusion once lingered. Waves no longer need to be physical ripples. Particles no longer need predetermined paths. What exists between preparation and measurement is a set of possibilities evolving smoothly, waiting to be expressed. This marks a decisive shift away from classical determinism. The future is no longer a single line extending forward, but a branching field of potential outcomes shaped by precise mathematical rules. Understanding this does not diminish reality, it deepens it. Probability in quantum mechanics is not a statement about ignorance. It is a statement about how nature works. Once this is accepted, the discomfort eases. What remains is a quieter, more flexible picture of the universe, one where certainty is not abandoned but redefined, emerging not from inevitability, but from consistency across countless individual events. Settle into the comfort of this structured potential. There is no pressure for a single path. You are part of a vast branching field of possibilities, held together by rules that are as steady as they are subtle. Let the weight of expectation dissolve into the quiet, predictable rhythm of the probable. To understand the statistical wave is to enter a world where the word wave describes not the motion of a physical substance like water or air, but the movement of information and possibility. When we look at a crashing ocean wave, we see a collective motion of trillions of water molecules, a physical hump of liquid moving across the surface. In the quantum realm, the waves we track are wave functions, mathematical descriptions that ripple through space and time, carrying with them the evolving likelihood of where a particle might manifest. This transition from physical waves to statistical waves is one of the most significant conceptual transitions in modern science. It replaces the idea of a solid object traveling along a single jagged line with the idea of a spread-out field of potential that follows smooth, rhythmic patterns. In this view, a particle is not a thing that is lost in the mist. It is a point of focus within a beautifully ordered distribution. The unpredictable nature of an individual event is cradled within the perfect predictability of the pattern as a whole. This is the heart of the statistical wave. It provides a stable, wave-like structure to a reality that refuses to be pinned down to a single path. Imagine a dark room where a single photon is released toward a screen with two narrow slits. In the classical mind, the photon must choose one slit or the other, like a marble falling through a pipe. But the statistical wave tells another story. The wave function of the photon spreads out as it travels, passing through both slits simultaneously. On the other side, these two parts of the wave interfere with one another, much like the ripples from two stones dropped into a pond. In some places, the waves reinforce each other, creating regions of high probability. Elsewhere, they cancel each other out, creating regions of zero probability. If we were to place a detector on the screen, we would see a single flash of light, one particle hitting one spot. At first, this single spot looks random, like a stray raindrop on a pavement. But as we continue the experiment, releasing thousands of photons one by one, a pattern begins to emerge from the darkness. The individual flashes do not cluster behind the slits. They arrange themselves into a series of bright and dark fringes. This is the interference pattern. Even though each photon arrived as a discrete particle, the collective distribution of those particles perfectly matches the shape of the statistical wave. This phenomenon reveals a deep, quiet truth about the nature of the unpredictable. While we cannot say where any single photon will land, we can say with absolute certainty what the final pattern W will look like. The unpredictability is not chaos, it is a freedom that exists within a very specific, disciplined framework. The statistical wave acts as a guide, a silent director that ensures that while individual members may wander, the group as a whole will always find its place. This relationship between the individual and the collective is what allows the universe to be both flexible and stable. It allows for the spontaneity of the quantum world without sacrificing the reliability of the macroscopic world. When you look at the stars, you are seeing the result of countless statistical waves reaching your eyes. Each photon is an unpredictable event, yet the image of the star is steady and clear because the probabilities are so perfectly balanced across the vast numbers involved. There is a profound sense of peace in this realization. The idea that even when the details are uncertain, the big picture is governed by an unwavering wave-like order. The mathematical beauty of these waves is their continuity. While the detection of a particle is a sudden discrete event, the wave function that governs it evolves smoothly according to the Schrödinger equation. This equation is the law of motion for the quantum world, and it is as deterministic as any law in classical physics. It tells us exactly how the field of probability will ripple, spread, and interact over time. This means that at the fundamental level, the universe is not rolling dice in a vacuum of structure. It is following a precise, wave-like choreography. The randomness we see is merely the moment when the continuous wave of potential meets the discrete world of measurement. It is the point where the many becomes one. By focusing on the wave rather than the particle, we can see nature's underlying harmony. We see that the universe is not a collection of jagged, broken movements, but a series of overlapping rhythmic vibrations. These vibrations are the source of all structure, from the energy levels in an atom to the chemical bonds that hold our DNA together. Everything rests on the shoulders of these statistical waves, which maintain the quiet consistency of reality. As you settle into the rhythm of this thought, imagine your own presence as a kind of statistical wave. Throughout your day, you occupy many different states, different moods, different tasks, different places. If someone were to measure you at any given moment, they would find you in one specific state. But the truth of who you are is not found in any single measurement. It is found in the overall pattern of your life, the wave-like distribution of all your possibilities. You are a coherent whole made of many fluctuating parts. In the quiet of the night, you can let go of the need to be this or that. You can allow yourself to be all wave, sprawling and peaceful. There is no urgency to collapse into a single point. You can simply drift through the interference patterns of your own mind, watching the peaks and valleys of thought rise and fall with the same discipline as the quantum fields. The uncertainty of tomorrow is not a threat because it is contained within the stable, predictable wave of your existence. You are governed by patterns that are far deeper than the surface noise of everyday life. There is a gentle humor in the fact that nature is so meticulously organized around the concept of maybe. We spend so much of our lives seeking absolute certainty, yet the very foundation of the universe is built on the elegant management of probability. By learning to trust the statistical wave, we are aligning ourselves with the way the cosmos actually functions. We are accepting that a range of possibilities is more real than a single rigid outcome. This acceptance brings a softening of the spirit. It allows us to view the unpredictable moments of our lives not as errors, but as the natural expression of a creative, wave-like reality. The pattern will hold, the fringes will appear. The structure of the universe is not at risk just because an individual particle takes an unexpected path. Settle into the vast, quiet reliability of the collective. The statistical waves are moving through you and around you, weaving the fabric of the night into a stable, rhythmic tapestry. As the exploration of the unpredictable continues, the discomfort of the unknown begins to fade into a deeper appreciation for the structure of likelihood. We see that the universe is like a grand symphony where every note is a probability, and the music as a whole is a masterpiece of consistency. Each note is free to be what it is, yet the symphony is never lost. As you drift towards sleep, let the image of these shimmering waves of potential fill your space. See them as calm, glowing lines moving through the darkness, intersecting and overlapping in a slow, eternal dance. There is no conflict here, only the quiet accumulation of individual events into a beautiful, coherent whole. The waves are steady, the patterns are true, and you are resting in the heart of a universe that is as disciplined as it is free. Settle into the probability of rest. Let the statistical wave carry you into a state of deep, structured peace, where every breath is a part of the pattern, and every dream is a possibility waiting to be explored. Uncertainty is often misunderstood as a kind of failure, a lack of precision, or a sign that something has gone wrong in the process of measurement. In everyday language, to be uncertain is to be unsure, to lack clarity, or to miss important information. It is tempting, then, to interpret the uncertainty principle in the same way, as a technical limitation that might be overcome with better instruments or more careful technique. That interpretation is comforting, but it is incorrect. In quantum mechanics, uncertainty is not a flaw in observation, it is a structural feature of how nature behaves at small scales. It does not arise because measuring devices disturb delicate systems, although disturbance can certainly occur. Rather, it arises because certain properties simply do not have exact values at the same time, no matter how they are probed. The most well-known example involves position and motion. In everyday experience, these feel inseparable. An object is somewhere, and it is moving in a particular way. With sufficient care, both can be measured precisely. Classical physics assumes this without hesitation. If the present state is known exactly, the future follows deterministically. Quantum mechanics places a quiet boundary here. The uncertainty principle states that the more precisely the position of a particle is defined, the less precisely its motion can be defined, and vice versa. This is not a statement about experimental clumsiness. It is a statement about the limits of definition itself. Nature does not allow both quantities to be sharply specified at once. This idea emerged in the mid-1920s through the work of Werner Heisenberg. During the formative years of quantum mechanics, physicists were struggling to reconcile wave-like mathematics with particle-like observations. Heisenberg's insight was to focus not on visual models, but on what could be meaningfully described and predicted. What he found was striking. Attempts to sharpen certain predictions inevitably blurred others. The math itself enforced this trade-off. No matter how the equations were arranged, the same constraint appeared. Precision in one domain demanded imprecisio in the other. It is important to be clear about what this does and does not mean. The uncertainty principle does not say that particles wander aimlessly or that anything can happen. The uncertainties involved are tightly constrained. They follow exact quantitative relationships that have been tested repeatedly. What is limited is not predictability in general, but simultaneous exactness. One helpful way to approach this is to think in terms of waves, not objects. A wave that is sharply localized in space must be composed of many different wavelengths. This mixture leads to uncertainty in how the wave evolves over time. Conversely, a wave with a single, well-defined wavelength spans space. The trade-off is built into the structure of waves themselves. Quantum systems behave in this wave-like manner at small scales. Position corresponds to how localized the wave is. Motion corresponds to how rapidly it changes. Trying to pin one down necessarily spreads the other. This is not a technological limitation. It is mathematical and physical. Common explanations sometimes describe uncertainty as arising because measurement disturbs the system. Shine light on a particle to see where it is, and the light knocks it around. While this can happen, it is not the core issue. Even in idealized situations where disturbance is accounted for, the uncertainty remains. The limitation persists even in principle. Another misconception is that uncertainty introduces randomness without structure. In fact, the opposite is true. The uncertainty principle is one of the reasons atoms are stable. If electrons could have both perfectly defined positions and perfectly defined motion, they would collapse into the nucleus. Uncertainty prevents this. It spreads the electron's presence in a way that allows atoms to exist at all. In this sense, uncertainty is protective. It imposes limits that make matter possible. Chemistry, materials, and life itself depend on it. The familiar world rests quietly on this rule, even though it contradicts classical intuition. There is also a tendency to interpret uncertainty as ignorance, as if particles secretly possess exact properties that are merely hidden. Decades of experimental work have challenged this view. Tests designed to reveal hidden deterministic variables have consistently failed to restore classical certainty. The probabilistic and uncertain structure appears to be fundamental, not provisional. This reinforces the shift introduced earlier. Probability is no placeholder for missing information. It is a core feature of the theory. The uncertainty principle formalizes this by showing that even the questions that can be asked are constrained. Some pairs of properties cannot both be sharply defined, not because answers are missing, but because the questions themselves exceed what nature allows. It is worth pausing on how radical this is. Physics for centuries aimed to describe the world in terms of exact values evolving smoothly over time. The uncertainty principle redraws the boundaries of description. It says that the universe is not built from perfectly specified trajectories, but from ranges, distributions, and limits on simultaneous definition. This does not make the universe vague. It makes it precise in another way. The uncertainties involved are not arbitrary. They are governed by exact relationships involving fundamental constants of nature. These constants set the scale at which quantum effects become noticeable. At the human scale, the uncertainties are so small that classical certainty reemerges naturally. This is why everyday experience feels deterministic, even though it rests on probabilistic foundations. Gentle humor can help here. Nature, it seems, insists on a little personal space. It refuses to be pinned down too tightly, insisting that if one aspect is nailed down, another must be allowed to breathe. The rule is firm but not hostile. It simply defines how close a description can get. Understanding this also resolves much of the confusion surrounding quantum measurement. Measurements do not reveal pre-existing exact values for all properties. They produce outcomes within allowed ranges. The uncertainty principle describes those ranges and the relationships between them. It is not a comment on human inadequacy but on natural structure. Scientific bodies and laboratories worldwide have verified these limits through countless experiments. From electron beams to ultra-cold atoms, the same patterns appear. Sharpen one quantity and the complement spreads. The effect is not subtle. It is robust, repeatable, and unavoidable. By addressing these misunderstandings directly, the uncertainty principle becomes less threatening. It is not an attack on knowledge. It is a clarification of its scope. It tells where certainty is possible and where it is not. And it does so with mathematical and experimental precision. This formalizes the probabilistic view introduced earlier. Probability describes the range of possible outcomes. Uncertainty describes the limits on how narrowly those ranges can be defined. Together they form a coherent framework, one that replaces classical determinism not with chaos but with structured openness. A quiet elegance in how this fits together. The universe does not conceal its behavior out of spite. It follows rules that are consistent, testable, and deeply interconnected. Uncertainty is not an admission of defeat. It is a boundary that allows the rest of the structure to exist. Once this is accepted, tension fades. The desire for absolute precision relaxes. What remains is a deeper appreciation for how nature balances definition and freedom. The uncertainty principle does not undermine understanding. It refines it, setting the stage for everything that follows from the probabilistic fabric already in place. In this light, uncertainty is no longer a problem to be solved. It is a principle to be understood. And once understood, it reveals not a universe slipping out of control, but one that is quietly, consistently, and beautifully constrained. Settle into this thought. Let the need to pin down every detail dissolve. Allow the universe its breathing room. You are part of a reality that is stable because it is not too rigid. You are safe within the protective boundaries of the uncertain. The night is quiet, the limits are set, and the world remains perfectly, beautifully in place. For much of scientific history, particles were treated as the basic units of reality, small solid points moving through empty space. Even as quantum mechanics complicated this picture, it was still tempting to imagine electrons, photons, and other particles as tiny objects with fuzzy properties. The language of particles lingered because it felt familiar. It matched everyday experience scaled down. Modern physics quietly lets go of that picture. At the deepest level currently understood, particles are not fundamental objects at all. They are events, ripples, localized excitations of something more basic that fills all of space. That underlying structure is known as a field, and quantum field theory is the framework that unites this idea. A field in this context is not a material substance. It is a continuous entity that exists everywhere, even in regions that appear completely empty. Temperature is a familiar example at human scale. It exists throughout a room, rising and falling smoothly from place to place. A magnetic field behaves. Similarly, stretching invisibly through space, influencing objects without occupying them. Quantum fields extend this idea to its most fundamental form. According to quantum field theory, every type of particle is associated with its own field. There is an electron field, a photon field, and fields for every other known particle. These fields are not optional additions. They are always present even when no particles are detected. What is normally called a particle is simply a localized disturbance in its corresponding field, much like a brief wave passing through an otherwise calm surface. This shift in perspective is profound. It replaces object-based thinking with process-based understanding. Instead of asking where a particle is, it becomes more accurate to ask how a field is behaving in a particular region. Instead of imagining objects moving through emptiness, reality becomes a tapestry of overlapping fields continuously interacting and occasionally producing detectable excitations. This framework grew out of the need to combine quantum mechanics with special relativity. Early quantum theory worked well for isolated systems, but it struggled to handle situations where particles could be created or destroyed, such as high-energy collisions. Experiments showed that particles could appear and disappear, converting energy into matter and back again. A theory built around permanent objects could not accommodate this behavior cleanly. Quantum field theory solved this by treating Ng creation and destruction as natural features. Fields can be exciting or calm. Energy added to a field produces particles. Energy removed allows them to vanish. Nothing fundamental is lost or gained. The field remains. This view underlies the standard model of particle physics, the most successful description of fundamental interactions currently available. The standard model organizes known particles and forces into a coherent framework built entirely from interacting quantum fields. Electromagnetism, the weak nuclear interaction, and the strong nuclear interaction all arise from field interactions governed by precise rules. The predictive power of this model is extraordinary. Calculations based on quantum field theory match experimental results to astonishing accuracy. Certain quantities have been confirmed to more than 10 decimal places. This level of agreement is not accidental. It reflects a framework that captures something deeply real about how nature operates. Experimental confirmation of this picture comes from some of the most ambitious scientific efforts ever undertaken. Facilities such as the Large Particle Accelerators, operated by international collaborations, provide direct evidence for field-based behavior. At CERN, particles are accelerated to enormous energies and collide, briefly disturbing the underlying fields enough to reveal new excitations. The results consistently support the field picture. New particles appear exactly where and when theory predicts. What is especially striking is that even empty space participates in this behavior. A region with no particles present is not inert. Fields are still there, fluctuating gently and constrained by quantum rules. These fluctuations can have measurable effects, confirming that fields are not abstract mathematical conveniences but physically active components of reality. This understanding deepens earlier ideas about uncertainty and probability. If particles are excitations of fields, then uncertainty is no longer just about missing information. It reflects the fact that fields themselves have intrinsic variability. Probabilities describe how excitations emerge from continuous structures, not how objects hide their properties. It also reframes earlier confusion about wave and particle behavior. Waves are not optional descriptions layered onto particles, they are expressions of how fields evolve. The spread of a probability distribution reflects the underlying field dynamics. When a particle is detected, it is not because a tiny object finally chose a location, it is because a field interaction produced a localized event. There is something quietly elegant about this. The universe is no longer a collection of things bouncing around in emptiness. It is a set of processes unfolding within ever-present structures. Fields interact, exchange energy, and produce the appearances we label as particles. Objects become moments. Stability becomes a pattern. Gentle humor fits here as well. The idea of particles turns out to be a useful illusion, like waves on the surface of the ocean being mistaken for separate entities. The waves feel real, behave consistently, and can be measured precisely. Yet, the deeper reality is the water itself. In quantum field theory, particles are the waves, and fields are the ocean. This perspective also explains why the same particle can be created in different places under different conditions, yet always behave identically. It is not because countless identical objects exist independently. It is because each excitation arises from the same underlying field governed by the same rules everywhere. Scientific institutions across the world continue to test this framework, pushing it into new regimes of energy and precision. So far, it has held up remarkably well. Where it succeeds, it does so decisively. Where it falters, it points clearly to the questions that remain open, particularly where gravity enters the picture. By replacing object-based thinking with field-based understanding, quantum field theory brings coherence to many of the strange features encountered earlier. Uncertainty, probability, and dual behavior all find a natural home within this deeper structure. The universe does not consist of tiny beads stitched together by force. It consists of fields continuously present, occasionally excited, and endlessly interacting. Once this shift is made, earlier discomfort begins to fade. The strange behavior of particles no longer feels like a series of exceptions. It becomes the expected behavior of a world built from fields rather than objects. And in that world, solidity, certainty, and individuality emerge not as fundamentals, but as patterns arising from a far richer and more subtle foundation. We are drifting through a cosmic ocean that is never truly still, but always profoundly ordered. Every atom in your body, every ray of light, is a note played on the strings of these universal fields. There is a deep peace to be found in the field perspective. It reminds us we are not isolated fragments in a cold void. We are integral parts of a continuous living tapestry. The fields that make up the distant stars are the same fields that make up your very heart. We are unified by the fabric of reality itself. In the quiet of the night, you can feel the subtle fluctuations of this tapestry. You are not a solitary observer, you are an excitation of the universe, a beautiful and temporary expression of fields that existed for billions of years. Let the idea of being a separate object dissolve into the more expansive truth of being a process. You are a flow, a rhythm, a localized shimmering in the infinite field of potential. As you settle into sleep, let the vastness of the fields comfort you. They are tireless, they are everywhere, and they are the quiet structure that holds everything together. There is no emptiness, only presence. There is no isolation, only interaction. The ocean is calm, the fields are steady, and you are resting in the heart of the tapestry. Settle into the process of rest. Let the ripples of the night fade into the deep, enduring stillness of the fields. Everything is connected, everything is consistent, and everything is exactly as it should be. Separation feels fundamental. Two objects occupy different places. They move independently. What happens to one does not instantly affect the other. This assumption is woven deeply into everyday reasoning, reinforced by distance, time, and the apparent isolation of things in space. Even earlier ideas about fields, continuous and overlapping as they are, still allow for local behavior where interactions diminish with distance. Quantum mechanics quietly unsettles this picture. There are situations where two particles cannot be described independently at all, even when separated by vast distances. Their properties become linked not because of ongoing interaction, but because they share a single quantum description. This phenomenon is known as entanglement, and it represents one of the most striking departures from classical thinking. Entanglement does not mean that particles communicate secretly or exchange signals faster than light. It means something subtler. The system must be treated as a whole. The state of one particle cannot be fully specified without reference to the other. What appears to be two objects behaving separately is at a deeper level one system expressing itself in two locations. This shared behavior arises naturally from the quantum framework already in place. When particles are created together or interact in specific ways, their properties become correlated. Measuring one reveals information about the other, not because information has traveled between them, but because the information was never separate to begin with. Consider a pair of particles produced in a single process. Their properties are linked by conservation laws. Before measurement, neither particle has a definite value for certain properties. Instead, the system as a whole has a well-defined structure. When one particle is measured, the system responds by producing a consistent outcome for the other, no matter how far apart they are. This is where intuition begins to struggle. Distance usually weakens influence. Here it does not. The correlations persist even when particles are separated by kilometers or more. Experiments have confirmed this repeatedly using photons sent through optical fibers in free space, measured by detectors operating independently and far apart. The key word is correlation. Outcomes are linked in ways that cannot be explained by shared history alone. Classical explanations suggest that particles might carry hidden instructions, predetermined responses that are merely revealed upon measurement. If that were the case, the correlations would obey certain statistical limits. They do not. In the 1960s, physicist John Bell derived a set of inequalities that any theory based on log all hidden variables must satisfy. These inequalities provided a clear experimental test. If measurements violated the inequalities, then no local explanation based on pre-assigned properties could account for the results. Experiments were carried out again and again with increasing sophistication and tighter controls. The inequalities were violated. The results were unambiguous. Nature does not behave as if entangled particles carry independent instructions waiting to be uncovered. Correlations are stronger than any classical local theory allows. This does not mean information travels instantly. It means that the underlying description is not built from independent parts. This is a crucial distinction. Entanglement does not allow faster than light communication. While measuring one particle affects the description of the system, it does not allow control over the outcome. Each individual result appears random. Only when results are compared later do the correlations become visible. No usable signal can be sent this way. This preserves consistency with relativity. Cause and effect remain bounded by the speed of light. What changes is not the flow of information, but the structure of description. The universe at small scales does not insist on separability as a fundamental principle. Seen through the lens of quantum fields, this becomes more intuitive. Fields extend throughout space. Excitations within them need not be independent if they arise from a shared process. Entanglement reflects the continuity of the underlying fields rather than the independence of the excitations. What appears as non-local behavior emerges naturally from a framework that was never fully local to begin with. This challenges the idea of objects as self-contained units. In the classical picture, objects possess properties internally, regardless of context. Quantum mechanics replaces this with a relational view. Properties are defined through interactions and shared states. Independence becomes an approximation, valid at large scales, but incomplete at small ones. There is a quiet elegance in this shift. It suggests that the universe is more interconnected than appearances suggest without being chaotic or uncontrolled. Entanglement does not collapse space or erase distance. It reveals that some features of reality are distributed across systems rather than residing in isolated pieces. Gentle humor helps soften the surprise. Entangled particles behave less like distant strangers and more like dance partners who learn the routine together and continue in sync long after the music has faded. No signals are exchanged. They simply remain coordinated because they were never separate in the first place. Experimental confirmation of entanglement has become routine in modern physics laboratories. Photons are entangled and sent in opposite directions. Measurements are made independently. Results align exactly with quantum predictions and consistently violate classical limits. These experiments are not rare demonstrations. They are standard tools used to test and refine understanding. The reliability of these results is what makes entanglement so important. It is not an exotic curiosity. It is a predictable feature of quantum systems. Technologies such as quantum cryptography rely directly on entanglement, using its correlations to detect interference and ensure security. The behavior is strange, but it is also dependable. This further reinforces the move away from object-based thinking. If particles were truly independent objects, entanglement would be impossible. The fact that it exists and reliably exists suggests independence is not fundamental. It is emergent, arising when interactions fade and correlations become negligible. At human scales, this emergence is complete. Objects behave independently, causes remain local, the classical world reasserts itself. At quantum scales, however, the seams remain visible. Systems retain memory of shared origins. Fields carry correlations across space without effort. Understanding entanglement requires patience, not reinterpretation of causality. Nothing travels faster than light. Nothing breaks the structure of space-time. What changes is the assumption that reality can always be divided cleanly into separate parts. This builds directly on earlier ideas about fields and probability. Probabilities apply not just to individual particles, but to entire systems. The wave description encompasses all entangled components at once. Measurement selects outcomes from the shared structure, producing results that appear local but reflect non-local organization. Once this is accepted, entanglement becomes less mysterious. It is no longer a paradox to be resolved, but a feature to be understood. The universe does not insist that everything be separable. It allows relationships to persist across distance, not through communication, but through shared description. In this way, entanglement quietly reshapes how reality is imagined. Objects are no longer the final units. Systems take precedence. Connections matter as much as components. Beneath the apparent independence of things lies a deeper coherence, patiently expressed through correlations that refuse to fade, no matter how far apart their expressions may appear. The stillness of the quantum whole is a profound comfort. It means that the universe has a memory, a way of staying in tune with itself across vast stretches of space. You are part of this interconnected fabric. Just as entangled particles share a single history, every atom in your being is part of a larger story that stretches back to the very beginning. You are never truly isolated. The connections are there, silent and invisible, woven into the fields that permeate everything. As you drift into sleep, imagine the universe as a calm, glowing web of these relationships. There is no distance that can truly sever the shared description of reality. You are held within a system that is vast, coherent, and deeply unified. Let the weight of isolation fall. You are resting in a field of connections, a participant in the shared rhythm of the cosmos. The dance continues, the correlations hold, and the universe remains a single, beautifully integrated whole. Settle into the quiet embrace of the entangled night. The connections are stable, the system is at rest, and you are part of the deep, enduring unity that defines the heart of the quantum world. Everything is in sync, and everything is at peace. Measurement sounds passive. Something is observed, a reading is taken, a value is recorded. In everyday life, measuring feels like a gentle act, a way of revealing what was already there. A ruler does not change the length of a table. A clock does not alter the passage of time. Observation appears separate from the thing being observed. Quantum mechanics quietly removes that separation. At small scales, measurement is not a neutral glance. It is a physical interaction. Energy is exchanged, systems become linked, outcomes are produced through contact, not revealed by inspection. Nothing mystical is required, and no special role is reserved for human awareness. What matters is not who looks, but what interacts. This distinction is essential because misunderstanding it has led to decades of unnecessary confusion. Popular accounts sometimes suggest that consciousness causes reality to crystallize or that particles behave differently when observed. These ideas are compelling, but are not supported by how quantum experiments actually work. Detectors do not need eyes. Screens do not need awareness. Atoms register outcomes just as effectively as people do. In quantum experiments, a measurement occurs when a system interacts with something large enough to leave a stable record. A photon strikes a detector, an electron triggers a signal, an atom emits light that is absorbed elsewhere. These interactions are physical processes governed by the same rules as everything else. No thought is required. The difficulty lies not in the act of measurement itself, but in how it fits into the broader description of quantum systems. Before measurement, systems are described by probabilities. After measurement, a specific outcome appears. The transition between these descriptions is what physicists call the measurement problem. It is important to note what this problem is not. It is not a question about human perception. It is not about when someone becomes aware of a result. It is about how a probabilistic description gives rise to a single event. Early architects of quantum theory were acutely aware of this tension. Niels Bohr, one of the central figures in its development, emphasized that quantum systems cannot be separated from the conditions under which they are measured. According to what became known as the Copenhagen interpretation, physical properties are not attributes carried independently by particles. They are defined through interaction. This does not mean that reality depends on observers. It means that descriptions depend on context. The arrangement of an experiment determines what can meaningfully be said about a system. Change the interaction and different properties become relevant. Bohr argued that it is a mistake to imagine quantum objects possessing a complete set of definite properties at all times. Some properties only become well-defined when measured. Others remain undefined, not because they are hidden, but because the situation does not allow them to exist simultaneously. This view aligns naturally with everything encountered so far. Probability replaces certainty. Uncertainty limits simultaneous definition. Fields underlie particles. Entanglement links systems across distance. Measurement fits into this picture not as an intrusion, but as participation. When a quantum system is measured, it becomes entangled with the measuring device. The system and apparatus form a combined whole. From the perspective of the apparatus, a definite outcome appears. In terms of the larger quantum description, the interaction has produced a stable correlation. This is why disturbance is not the right word. Measurement does not simply knock a system out of its natural state. It creates a new state that includes both system and measuring device. The outcome is not uncovered. It is produced through interaction. A helpful everyday analogy is conversation. Words do not exist as fixed objects waiting to be discovered. They arise through interaction between speakers. Once spoken, they become part of the shared environment. The measurement is similar. It is an event that brings something into being within a particular context. This perspective also dissolves much of the confusion surrounding collapse. The idea that a wave function suddenly collapses can sound dramatic, even violent. In practice, it describes the transition from a probabilistic description to a definite record. Once an outcome is recorded in a stable way, probabilities are no longer required to describe that particular event. Nothing special happens at the moment of human awareness. The result exists once it is physically registered. Consciousness enters later, reading a result that has already taken place. This understanding is supported by countless experiments. Automated detectors register quantum events without supervision. Data is stored, analyzed later, and compared across laboratories. The results do not await observation. They are produced by interaction, and preserved by physical systems. Measuring issues remain an active research area, not because measurement is mysterious, but because the boundary between quantum and classical descriptions is subtle. Large systems behave classically not because quantum rules stop applying, but because interactions spread information so widely that probabilistic descriptions become effectively irreversible. Once information about an outcome is dispersed into many degrees of freedom, the system behaves as if a single result has been selected permanently. This is why measuring devices appear classical. They are designed to amplify tiny events into robust records. Understanding measurement in this way also clarifies its relationship to entanglement. Measurement is a special case of entanglement, where one part of the system is large, stable, and capable of recording outcomes. The correlations produced become one-sided, favoring definite records over reversible evolution. Gentle humor fits here too. The universe does not wait to be noticed. It does not pause politely until someone looks. Measurements happen because things bump into other things, exchange energy, and leave traces behind. Awareness arrives afterward, like reading yesterday's news. Stabilizing the concept of measurement removes a great deal of unnecessary tension from quantum mechanics. There is no need to invoke consciousness as a causal agent. There is no need to imagine reality flickering in and out of existence. There is only interaction governed by precise rules, producing outcomes that become part of the physical world. This view also restores continuity with the rest of physics. Measurement is not a special category reserved for quantum systems. All measurement at every scale involves interaction. The difference is that at small scales, interaction cannot be ignored or treated as negligible. Seen this way, measurement is no barrier to understanding quantum reality. It is one of its most revealing features. It shows how possibilities become events, how probabilities give way to records, and how the abstract structure of the theory connects to the concrete world. By emphasizing participation rather than disturbance, measurement becomes less threatening and more coherent. It is not an act of interference that breaks a delicate system. It is the natural way systems relate to one another. Once this is appreciated, the lingering mystery softens. Measurement is no longer the point where physics gives up. It is the point where interaction becomes visible, and in that visibility, the quiet logic of quantum mechanics continues to hold, consistent, testable, and firmly grounded in the physical world. As you drift towards sleep, consider the quiet interactions taking place all around you, the air molecules brushing against the walls, the light from a distant star striking a window pane, the gentle pressure of your body against the bed. Each is a form of measurement, a silent participation in the unfolding of reality. You are no stranger to watching from outside. You are a participant woven into the fabric of these interactions. There is no need to be observed to be real. You are real because you interact, because you are part of the shared state of the universe. The night is full of these quiet records, these stable outcomes of a world that is always in conversation with itself. Settle into the deep physical presence of your own being. The interactions are steady, the records are firm, and you are a vital part of the quiet order that defines the night. Quantum mechanics has an unusual reputation. It is one of the most successful theories ever developed. Yet it is also one of the most debated, not because its predictions fail, but because its meaning remains open to interpretation. This combination can feel unsettling. In most areas of science, disagreement signals uncertainty or incomplete understanding. Here, disagreement persists, even while the maths works flawlessly. The reason is subtle. Quantum mechanics is extraordinarily clear about what will be observed. It is far less explicit about what is happening in between. Quantum theory equations describe how probabilities evolve over time. They specify how systems behave when they interact and what outcomes will be produced. These rules have been tested for over a century and confirmed with remarkable precision. Wherever experiments have been performed carefully, the results align with the same mathematical framework. And yet that framework allows more than one way of telling the story. This is why multiple interpretations exist. The maths does not dictate a single narrative about what reality is doing when it is not being measured. It tells how to calculate results, not how to imagine the underlying process. Different interpretations step into that gap, offering distinct ways of thinking about the same formal structure. One of the earliest and most influential approaches is commonly known as the Copenhagen interpretation, associated with figures such as Niels Bohr. It emphasizes the role of measurement and context. In this view, quantum systems do not possess definite properties independent of interaction. Physical quantities become meaningful only when measured, and the theory concerns what can be said about outcomes, not what exists unobserved. Copenhagen thinking is often pragmatic. It does not attempt to describe an underlying mechanism behind the equations. Instead, it treats the mathematical framework as complete in itself. Questions about what happens between measurements are considered undefined or unnecessary. This approach has the advantage of restraint. It avoids adding assumptions beyond what experiments require. For some, however, this restraint feels unsatisfying. The desire to describe an objective reality unfolding continuously has a long history in physics. This motivation gave rise to alternative interpretations that retain the same maths while telling a different story. One such approach is the many worlds interpretation proposed by Hugh Everett in the 1950s. Instead of treating measurement as a special event where probabilities collapse into a single outcome, this view suggests that all possible outcomes occur. Each outcome corresponds to a different branch of the universe, all evolving according to the same underlying equations. In this picture, probability reflects the relative weight of these branches rather than the probability of a single outcome. There is no collapse. The wave description continues smoothly and universally. Measurement becomes a branching process rather than selection. This idea can sound extravagant, even overwhelming, yet it does not introduce new maths. It takes the existing equations at face value and applies them universally, including to measuring devices and observers. Its boldness lies in interpretation, not prediction. At the other end of the conceptual spectrum lies pilot wave theory, associated with David Bohm. This approach reintroduces determinism by proposing that particles have definite positions at all times, guided by an underlying wave. The wave evolves according to standard quantum equations, while particles follow precise trajectories influenced by it. In this view, probability arises from ignorance about initial conditions rather than fundamental indeterminacy. The wave provides the structure, the particle provides the outcome, both coexist, linked by clear rules. Pilot wave theory restores a sense of continuous motion and objective reality. However, it does so at a cost. It requires non-local influences where changes in one part of the system can affect distant parts instantaneously. While this does not allow faster-than-light communication, it challenges intuitive notions of locality. What is remarkable is that all of these interpretations agree on what experiments will show. Whether one prefers Copenhagen restraint, Everett branching, or Bohmian guidance, the calculated probabilities are identical. No experiment currently distinguishes between them. This is no weakness of quantum mechanics. T is a reflection of its completeness. The theory provides all the information needed to predict outcomes. The interpretations differ only in how that information is framed conceptually. This distinction between physics and philosophy is essential. Physics concerns testable predictions. Philosophy concerns meaning, explanation, and intuition. Interpretations belong primarily to the second category. They influence how the theory is understood, taught, and imagined, but they do not alter its empirical success. This is why debates about interpretation can persist indefinitely without being resolved by experiment. They are not disagreements about facts. There are disagreements about how to narrate those facts. There is a temptation to treat one interpretation as more correct than the others. Often this preference reflects personal taste. Some find comfort in minimalism, others prefer realism, some are drawn to determinism, others accept indeterminacy as fundamental. Math remains indifferent to these preferences. Gentle humor helps here. Quantum mechanics is like a perfectly accurate recipe that refuses to explain why the dish tastes the way it does. Different cooks invent different stories about the flavor, but the meal comes out the same every time. Understanding this can be liberating. It removes the pressure to choose the right interpretation. One can work effectively with the theory without committing to a particular metaphysical stance. Many practicing physicists do exactly that, using the maths daily while remaining agnostic about its deeper meaning. This also reframes earlier debates about measurement. Whether one views measurement as collapse, branching, or guidance, the observable results are the same. The differences lie in how one imagines the unseen processes connecting preparation to outcome. By separating physics from philosophical framing, much of the tension surrounding quantum mechanics dissolves. The theory does not demand belief in any particular story, it demands only that its rules be followed when making predictions. This separation also reflects scientific humility. Quantum mechanics tells what can be known and calculated with extraordinary precision. It remains silent on certain questions, not because it is incomplete, but because those questions may not have operational meaning within the theory. Seen this way, multiple interpretations are not a sign of confusion, they are a sign of flexibility. The same mathematical structure supports different ways of thinking, each consistent with observation. The universe, it seems, is content to be calculated correctly without insisting on a single explanation. The equations do their work quietly and reliably. The stories built around them remain optional, and in that quiet separation between calculation and interpretation, quantum mechanics reveals something subtle. Understanding does not always require agreement on meaning. Sometimes it requires only that predictions be precise, experiments be honest, and expectations remain open to more than one way of seeing the same underlying structure. As you drift toward rest, let the weight of these many stories soften. You do not need to choose a path through the branching possibilities. You can simply exist within the whole structure. Whether the universe is a single path of probability or a vast forest of many worlds, the quiet consistency of the night remains the same. The stars shine with a reliable light, the air moves with a gentle rhythm, and your heart beats with a steady pulse. You are a part of a reality that is far deeper than any one story we tell about it. Settle into the calm, mathematical grace of the universe. The equations are balanced, the results are certain, and you are at peace within the vast, flexible architecture of the night. Space feels like the quietest thing imaginable. It stretches calmly between objects, offering room to move, room to exist, and room to separate one thing from another. In everyday experience, space behaves like a stage. Events happen within it, but it does not appear to participate. It does not react. It does not change simply because something passes through. For a long time, physics shared this intuition. Classical descriptions treated space as a passive backdrop, a fixed arena in which matter and energy played out their interactions. Even when space and time were woven together through relativity, space-time still behaved smoothly, bending in response to mass and energy, but remaining continuous and well-defined at every point. Quantum theory quietly raises the possibility that this picture too may be incomplete. If matter and energy are governed by quantum rules, and if gravity responds to energy and mass, then it becomes natural to ask whether space itself might also possess a quantum structure. Not merely a smooth container, but something with its own microscopic behavior, hidden beneath the calm surface, perceived at large scales. This idea does not arise from speculation alone. It emerges from the tension already encountered. Quantum mechanics treats time differently from space. Relativity binds them tightly together. If time resists clean integration into quantum theory, then space likely does as well. The two are not easily separated. One possibility explored by physicists is that spacetime is not infinitely smooth. At extremely small scales, far beyond direct measurement, it may have a discrete or granular structure. Not chunks in the everyday sense, but fundamental units of geometry, arranged in patterns that cause smooth space only when viewed from far enough away. This is a delicate idea and must be handled carefully. There is no experimental confirmation yet, but it is motivated by the same logic that led to quantization elsewhere. Smooth assumptions fail at small scales. Discreteness emerges where continuity once seemed obvious. Space-time fluctuations are one way to imagine this. At very small scales, geometry itself may fluke, changing subtly from moment to moment. Distances could vary slightly, angles could blur. These variations would be utterly negligible at the human scale, completely invisible to ordinary measurement, yet significant when probing the deeper structure of reality. The term space-time foam is sometimes used to evoke this idea. Though the imagery can mislead, nothing is bubbling or churning in a dramatic sense. The fluctuations are not chaotic. They are constrained by rules, just as quantum uncertainty constrains particles and fields. The image is meant only to suggest that space is not perfectly rigid when examined closely enough. One approach that explores this possibility is known as loop quantum gravity. In broad terms, it attempts to describe space as composed of tiny quantized loops, or networks woven together to form geometry itself. Distances and areas arise from the relationships between these loops rather than existing independently. The appeal of this approach lies in how it treats space as an active participant rather than a passive container. Geometry becomes something that can evolve, interact, and respond much like other physical systems. Space is no longer just where things happen, it is part of what happens. It is important to emphasize caution here. Loop quantum gravity is one of several competing approaches, and none has yet been confirmed experimentally. The details remain under development. What matters for now is the shift in perspective it represents. CE is no longer assumed to be smooth and continuous by default. That assumption is being questioned. This questioning mirrors earlier developments. Matter turned out not to be solid, energy turned out not to be continuous, light refused a single identity, probability replaced certainty, time lost its simplicity. In each case, the breakdown of intuition led not to disorder but to deeper structure. Space may be following the same path. If space has quantum properties, then distance itself may be subject to fundamental limits of definition. Just as position and motion cannot both be perfectly specified, geometry may resist infinite precision. This would not mean that rulers become unreliable or that buildings wobble unpredictably. It would mean that, at scales far beyond practical concern, the concept of distance reaches a natural boundary. This complements the earlier discussion of time. If time becomes unclear at quantum scales, it would be surprising if space remained untouched. Together they form space-time, and it is reasonable to expect that both share in whatever deeper structure lies beneath classical description. There is also a conceptual elegance in this idea. It avoids treating space as something separate from the rest of physics. Instead, space becomes part of the same story, governed by rules, subject to limits and capable of change. This unifies geometry with matter and energy rather than isolating it. Gentle humor can be found in how stubborn the backdrop turns out to be. Space, once imagined as the ultimate passive observer, may have been quietly participating all along. Not loudly, not dramatically, but with the same disciplined subtlety seen elsewhere in quantum physics. Avoiding speculative certainty is essential here. These ideas are not settled facts. They are informed attempts to reconcile theories that work extraordinarily well in their own domains but resist combination. The universe has not yet revealed whether space truly comes in quantum units or whether a different resolution awaits discovery. What can be said with confidence is that treating space as purely passive no longer feels adequate. The success of quantum field theory, the persistence of uncertainty, and the tension with relativity all point toward a more active role for geometry. Scientific institutions around the world continue to explore these questions using mathematical insight, theoretical consistency, and indirect experimental clues. The work is careful and incremental. There are no shortcuts here and no dramatic declarations. For now, the most important shift is conceptual. Space is no longer taken for granted. It is no longer assumed to be an empty stage. It is considered a candidate for deeper structure, one that may share in the same quantum principles governing everything else. This challenges a deeply ingrained habit of thought. It invites a quieter, more flexible view of reality, one where even the emptiest regions of the universe are not truly in RT, but structured in ways that only reveal themselves when intuition steps aside. Seen alongside the uncertainty surrounding time, this idea forms a coherent extension rather than a rupture. Space and time together become part of the question, not the unquestioned foundation, and in that shift, the universe once again reveals itself not as less understandable, but as more subtle than it first appears. As you listen to these words, imagine the room around you not as a hollow box, but as a living, breathing fabric. The very distances between you and the walls, or you and the ceiling, are not just empty numbers, they are manifestations of an underlying geometry that is dynamic and interconnected with everything else in existence. In the quiet of the night, the stage itself is part of the performance. There is no void, there is only the continuous, subtle activity of space-time. Settle into the comfort of this presence. You are resting on a surface that is not just solid, but deeply participant in the laws of the cosmos. The geometry is stable, the backdrop is firm, and the stage is perfectly set for rest. There is no need for space to be anything more than it is now. It is holding you, it is surrounding you, and it is behaving with an ancient and unwavering consistency. As the mind wanders toward the edges of what is known, the vastness of space becomes a source of peace rather than a source of coldness. If space is part of the quantum story, then even the farthest reaches of the universe are built from the same principles as the atoms in your own hand. The void is replaced by a shimmering, structured presence. There is a deep, quiet integrity to this view. It suggests that the universe is whole, from the smallest granular unit of space to the furthest galaxy. Everything is part of the same disciplined tapestry. As you drift towards sleep, let the boundaries of your surroundings soften. Imagine yourself merging with the calm, active fabric of the night. You are part of the geometry, a localized knot of energy and focus within the vast, participating backdrop of space-time. The ripples are gentle, the swaying is balanced, the stage at peace. Settle into the deep, rhythmic stillness of the universal arena. The backdrop is steady, the participants are resting, and the night is unfolding with the quiet grace of a reality that is perfectly at home within its own structure. Standing at the edge of quantum understanding does not feel like standing before a void. It feels more like pausing at a shoreline, where familiar ground gives way to deeper water, and where the surface remains calm, even as unseen structures extend below. After following quantum ideas through uncertainty, probability, fields, entanglement, and limits, what remains most striking is not how unstable reality becomes, but how reliably it holds together. Again and again, quantum mechanics has shown that while intuition may falter, structure does not. Measurements produce consistent outcomes. ND predictions align with experiment. Technologies built on quantum principles function with extraordinary dependability. Whatever reality may be doing beneath the surface, it does so with discipline. This reliability is easy to overlook amid discussions of interpretation and mystery. It is tempting to focus on what is unresolved, on questions that remain open, or descriptions that feel incomplete. Yet every experiment ever performed within the domain of quantum mechanics has returned results that fit the same underlying framework. The theory does not wobble when interpretations diverge. It does not depend on agreement about meaning to function correctly. Measurement is central to this stability. When quantum systems interact with the world, outcomes appear. Detectors register events, records form. These processes are not vague or ambiguous. They are repeatable physical interactions that behave the same way every time the same conditions are prepared. Whatever philosophical story is told around them, the measurements themselves remain firm. This is an important anchor. It means that reality does not change depending on how it is interpreted, whether one prefers to think in terms of collapse, branching, guidance, or contextual properties. The observable world remains the same. A photon is detected, an electron leaves a trace. An atom emits light at a specific frequency. Interpretation reshapes understanding, not outcome. This separation is quietly reassuring. It suggests that the universe is not waiting for consensus before behaving properly. It follows its rules regardless of how they are described. Human frameworks adjust, reality does not. Earlier discomfort with uncertainty often stems from the fear that a lack of certainty implies a lack of structure. Quantum mechanics demonstrates the opposite. Uncertainty limits what can be defined simultaneously, but it does so in a precise way. Probability governs outcomes, but it does so with exact distributions. Fields fluctuate, but within strict constraints. Even the vacuum behaves according to rules that can be measured and tested. Standing here, it becomes clear that quantum theory is not a story about instability. It is a story about limits that protect coherence, about rules that allow variation without collapse, and about a universe that resists being pinned down too tightly, yet never drifts into chaos. The diversity of interpretations reflects this resilience rather than undermining it. Different conceptual lenses can coexist because the mathematical structure beneath them is solid. The equations do not argue among themselves, they produce results. The debates arise only when human language tries to describe what the equations imply beyond what can be measured. There is a quiet humility in accepting this. It allows understanding to remain open without becoming anxious. Not every question needs an immediate answer. Not every gap signals failure. Some gaps simply mark where language, imagery, or intuition have reached their limit for now. This openness is not passive, it has always driven progress. Each time quantum mechanics revealed something counterintuitive, it did so through careful experiment. Each time confusion arose, it pointed toward deeper structure rather than emptiness. The pattern suggests that what lies beyond current understanding is unlikely to be arbitrary or chaotic. It will likely be constrained, consistent, and precise in ways that are not yet visible. Standing at the quantum edge also highlights how much has already been learned. Matter is not solid in the way it appears, yet it is stable. Energy is discrete, yet it flows smoothly at large scales. Light does not fit a single category, yet it behaves reliably. Space and time grow subtle at extreme scales, yet everyday experience remains coherent. Even emptiness happens to be structured. None of this diminishes the world, it enriches it. Gentle humor finds its place here as well. The universe, for all its complexity, seems remarkably patient with misunderstanding. It allows humans to use simplified models where they work, and it reveals deeper layers only when pushed carefully by experiment. It does not demand immediate comprehension, it waits. What matters most at this edge is not arriving at final answers, but recognizing how understanding evolves. Physics has never advanced by closing questions prematurely. It advances by learning which questions can be answered precisely, which must be reframed, and which are best held open for now. Reality remains stable throughout this process. Atoms do not flicker out of existence because interpretations differ. Technologies do not fail because debates continue. The moon does not vanish when unobserved, nor does light refuse to behave when no one is watching. The universe continues to operate according to rules that have proven extraordinarily robust. This stability allows curiosity to be gentle rather than urgent. There is no need to force resolution. The quantum world does not ask to be solved in one sweep. It invites careful attention, repeated testing, and patient revision of assumptions. Standing here, the arc of the journey becomes clear. Intuition was challenged, not discarded. Certainty was softened, not destroyed. Objects gave way to processes. Independence gave way to relationships. Determinism gave way to probability. At each step, something familiar was loosened and something deeper took its place. What remains unresolved is not a failure of understanding, but its frontier. The edge of quantum theory is no wall. It is a boundary shaped by current tools, current questions, and current language. Beyond it lies further structure, still hidden, still forming, still consistent with everything that has already been confirmed. Closing without finality means allowing that boundary to remain visible. It means resisting the urge to declare completion where none exists. It means recognizing that knowledge can be strong without being total. In this sense, standing at the quantum edge is not an ending. It is a pause, a moment to look back at how much coherence has emerged from what once seemed strange and to look forward without urgency to what remains to be understood. The universe does not demand certainty to function. It does not require final explanations to remain stable. It simply continues, governed by rules that are precise enough to build worlds and flexible enough to surprise those who study them. And so, understanding remains open, not unresolved in a troubling way, but unfinished in a productive one. The quantum edge holds firm beneath the feet, even as it stretches onward into deeper questions, inviting continued exploration without ever threatening the quiet reliability that has carried everything this far. As you drift into the final layers of sleep, let the structured horizon of the universe be your sanctuary. You are resting in a reality that is bounded by law and light, a world where even the unknown is a place of order. There is no chaos in the dark, only the silent mathematical grace of the fields. Your breath is a rhythm, your heart is a steady pulse, and your presence is a stable event in the vast tapestry of the cosmos. The horizon is wide, the journey is long, and the peace is absolute. Settle into the deep, enduring stillness of the quantum night. Boundaries are set, rules are firm, and the world is at rest. You are safe at the edge of knowledge, cradled by the consistency of a universe that is forever, reliably itself.